Okay, can I ask people to come in, sit down, enjoy? I'm going to announce right at the very beginning, we are already recording. So this is being recorded for a webinar that will then sit on the MASTS website and hopefully, if I'm pronouncing it correctly, the TESIS website for the Americans. So anybody who wants to modify their slides, let us know. Okay, and anybody who says anything, know that you're being recorded. So the microphone that is recording is right in front of me. So for the speakers, can you please sort of stand in this spot so that it's recorded? Also, once we have questions coming from the audience, please do then repeat that question so that the audience on the webinar can hear you. Okay, thank you very much. Great to see you all. Hopefully this is going to be a really fun, exciting day with lots of knowledge exchange. So yes, you're all here to listen about ecologists and engineers working together. And so this morning we have a very open session of some 15-minute presentations and then very short 5-minute presentations from some of the students and postdocs. And then we'll have close to an hour of discussion for each of these things, and then a break for tea in between, and then lunch. And this afternoon will be the TeraWatt talks in succession. Okay, so to kick off, indeed, we all know working in renewables is not the best of times, it's not the worst of times. So I was really glad to see that Scottish Renewables publication that just came out, which I took some slides from, is there's still a lot going on, but we need to be careful. We are sitting on a knife edge of where things are going to go, and it's kind of up to a lot of us in the room here to make sure things are going as well as they can. The good thing is things are really happening. So indeed, MyGen finished their cable laying last week, and that's all else is going on schedule. So really, all else I'm going to say is I'm going to pass over to Ben Wilson, who's going to chair the first session, and we're going to listen to the first sessions about the effects of engineering on ecology, and the second session's ecology on engineering. And hopefully, in between, we'll have a lot of dialogue. So we'll see how it goes. If there's a lot of questions and it's interaction at the front here, that's great. So we'll have most of the questions. We can have questions after the first speaker, and then the set of 3 talks quickly, and then questions after that. We'll see how those go, and if people would rather than sit and really talk in groups, we're set up in this situation with the cabaret style to do that as well. So we'll just see how it goes, whether we want a big room discussion or some individual discussions. And there should be a member at each table of our team that is recording and taking notes about these discussions that we'll collate at the end. Okay, and then this afternoon, like we say, John Side's group is going to, and the TeraWatt Project is going to give their talks. Okay, so here we go to engineering impacting ecology, and I'm going to invite up Tim Stallard, if I'm saying it correctly, sorry, from Manchester to give us our first talk, and hand over to Ben.
I think you just said my line. I'm just going to introduce Tim Stallard from the University of Manchester. And very excited to bring him here because he's a real engineer with blue tanks and stuff like that. So
and models and everything. And models and everything.
And models and everything. And, so I'm just going to leave it to him. But he's got a fantastic title: Engineering Models for Tidal Stream Turbine Waves, and Impact Ecological Aspects.
Okay, thanks Ben, and thanks all for having me here today. Very kind to call me a real engineer. I'm not entirely sure that's a compliment, but we'll see. You can comment later. Okay, so I'm going to give a little bit of background to where I'm coming from, which is where the wakes and waves bit come in, a bit of a fly-through of our work in that area. But the main focus of this is going to be impacts on turbine blades, some modelling work and some experimental work we've done in that area. So just a few slides on the first aspect first. This is basically what we're interested in as engineers in this area, modelling the loading of turbines in arrays. Okay, but actually that's relatively complicated because we need to be able to model the ambient flow, which is quite turbulent. We need to be able to model the wakes of individual turbines and the effect on other turbines, the global wake of the array and the effect of that on the coastal scale flow, and the effect of waves on individual turbines within the arrays. So there's a number of problems that we've tried to break down within this. So on ambient on-flow turbulence, we've done quite a lot of work on an EPSRC project and a readout project, ETI funded, looking at reproducing field measurements from the EMEX side. So those are measurements on the right, and the green line is our modelled profile of the velocity, but also we can predict, well, rather model the Reynolds stresses and the length scales of the turbulence. So we do modelling massively parallel computations of flows that are turbulent and unturbulent, structured turbulent in this case, the effect of those on turbine wakes and on unsteady loading. And this has been evaluated against 1 megawatt turbine data from the Alstom turbine at EMEC. That's for individual turbines. For arrays of turbines, that's not computationally tractable. So we have more efficient computational models for this, embedded RAND BEM type models, which are useful for modelling groups of turbines such as this. This is the wake of 12 turbines, which we might then look at embedding in coastal scale models, such as done by the Swansea group, Edmonds et al, down the bottom right there for a group of 5 turbines. But what's important, we think, is how accurate these things are, and not just the flow velocities, but the turbulence characteristics of these flow fields, because that's what affects the mixing at larger scales in coastal regions. So we've done quite a large amount of work with evaluating the accuracy of such models. I'm just showing a plot here of discrepancies of load prediction and discrepancies of wake prediction, but similar comparisons have been conducted for turbulence parameters and Reynolds stresses and similar. Okay, we've also looked at wave propagation over wakes. I guess other groups here have probably done similar things. That's a flow field. This is measurements of waves across a wake, looking at reduced wave height across the wake region and increased height either side of the wake, and comparison of that to spectral type models, where we get the broad agreement over the wake region and part of the bypass region, but not reduction across the shear region. But that's a sort of first pass, and we've looked at that for larger scale arrays as well. Okay, that will feed on to some of the discussion later, hopefully. So wave loading is important on turbines, turbulence loading is important on turbines, and we've done experimental campaigns to evaluate both of those. One of the main challenges we think in addition to those is modelling impact loads. So quite a challenging impact is something like that, bottom right. Minke whale, which we understand goes through locations where tidal stream farms will be deployed, impinging on our 3-bladed type turbines here. So we can more or less quantify the wave-induced loads on these turbines and the turbulence-induced loads. And what we were interested in is how can we model these deformable bodies impinging on rigid blades of turbines. Not actually very many methods available to be able to do that, because you want a modifiable body and a forced rotation of the turbine, or preferably longer term, a responding turbine. So the type of models that I'd shown before, you can track particles through them, but they don't necessarily respond to the flow in the correct way, particularly when they're large bodies relative to the turbine blades. Okay, so we've developed, or group, this is not personally myself, but colleagues at Manchester have further developed a method called SPH, smooth particle hydrodynamics, which has been well validated for free surface flows, particularly violent free surface flows where there's rapid deformation of the surface, which you can't capture with established methods or meshed methods. And incorporating additional types of particles in this method that are solid particles, effectively, that are connected not by the properties of a fluid, but by a lattice of springs connected to adjacent elements. So those are the green particles in the diagram on the right. And then the red particles are an interface between the fluid particles and the solid particles. But effectively, we've got a cloud of points, not a mesh, a cloud of points that have an assigned set of properties. Okay? This has been validated for just the spring part, because the SPH part had already been quite well validated for analytic cases of beam deflection and for sphere deformation, and there's publications on those which I can point to if of interest. But what we're particularly interested in then is, can we use this to model the response of something like this to a turbine? So Ben has provided information on the characteristic properties of different parts of whales and typical dimensions. And we use these material properties, the Young's modulus and the Poisson's ratio, to specify the properties of those green particles on the prior diagram. Okay, and then to pass them on to real turbine geometries, preferably representing lab experiments longer term. Okay, so we've got typical dimensions. So the question then was, well what geometry to use? So an idealized geometry is obviously very useful for comparison to test cases, and I'll come on to that in just a moment. As a initial demonstration of the capability of this, though, Peter and Ben, who were leading this work, decided to be quite ambitious and actually try and model a real skeleton. I understand that this is in Edinburgh Museum. So they got a scan done of this skeleton and converted that into a cloud of particles, which is what we see there. Wrap that cloud of particles in an envelope of particles that have the properties of blubber. So the central spine there and the skeleton has the properties of bone, the Young's modulus and Poisson's ratio of that. And the outer cloud has the properties of blubber, and there's a layer of particles that have the properties of skin on the outside. Okay, so that can be modelled because it's a mesh-free approach. We've just got effectively a cloud of particles within the volume that was scanned. When we get to a model then that's a bit like this, we have our fluid domain, which is all the blue dots, a rigid turbine. This is the geometry of a real turbine, a lab-scale turbine in this case, and a representative body here with the structural properties applied. What this then allows us to do, let's hope this actually works. It worked when we checked this before. Yes, there we go. We've got a deforming body then with its stiffness characteristics defined across those cloud of points. We've got a forced rotation of the turbine, and then it's impinging with the blade. And the turbine is also modelled as these cloud of green points, so it's rigid, but its motion is imposed. And therefore, as the blade points get close to the cloud of points that represent the whale, there's interaction between those two and deformation as a result. Okay, so obviously looks very smooth type of motion, but is it right? What we're interested with these methods is obviously validation. Okay, so other part of this work then has been to start to develop experimental methods and idealized cases that we can use for validation. So what we wanted to be able to do is have a body that represents the characteristics of a whale there, but simplified enough to be able to reproduce in experimental approaches. So here we've got a rigid turbine again, exactly the same as previous, and an idealized body with material properties selected so that we can produce them at lab scale, an aluminium spine, as we'll see in a moment, and a rubber skin around the outside. So the impact of that, we can now get quantitative predictions of the impact. This is just a time series of the impact load on a point on the blade. Looks kind of like you might expect an impact trace to look, but we don't yet know whether that's exactly right. So some experimental work has been conducted, but we're still to compare this directly across. So I'll just give a few slides on our experimental approach. So what we'd wanted to do initially, well, longer term, we'd still like to do, is produce this type of body that has material properties representative of the key features of that real whale that we looked at before. So an aluminium rod of a particular dimension that gives appropriate characteristics for the longitudinal stiffness. Ballistic gel was identified as an appropriate property material to represent blubber. And these high HDPE materials were appropriate for the harder material at the upper third or the front third of the body. So that was considered as a body to use as a target for a turbine that we developed for wave and wake loading, turbulence wave and wake loading, a 1.2 metre diameter of which you see a cross section there. But before we passed that at the turbine, we wanted to know a bit better how large these loads were relative to the wave and the current induced loads. So just to give it an indication to start with, this is a 1.2 metre diameter turbine. The blades are designed for peak wave load and for peak flow load. And that's a tip load on the blades equivalent to a bit under 100 newtons as a tip load on the blades. We'll come back to that in terms of the magnitude of impact loads in a moment. So before passing a target like that at turbines, we did a series of tests with a dry impact test rig. So this is a target down here, a blade, or an arm representing a blade, and a force transducer at the base. I've only got a few more there. Measured impact loads from different target types, so this is with skin and without, top right, and these are quite large loads, so of the order of tens of kilonewtons rather than the 100 odd newtons that we were looking at in terms of the peak load from flow and waves. And slightly surprisingly, there was limited variation with mass. These are repeat cycles with increasing masses, factor of 3 increase of mass across those. So general conclusion from those, low variation with mass, and reduced significantly by the presence of a softer skin material. So those are the sort of two initial trends from those. I still took no account of blubber, and forces are reduced substantially again by a deformable target. So the one on the right there is a target that's deformable with a rubber skin and then a ballistic gel core. And again, a substantial reduction of force, but still on order of 2 to 3 times those of the peak load due to wave and current, as estimated from the modelling prior to the design of the experimental equipment. So as yet, the wet version of these tests has not been conducted. So the impact is just with a stationary target. We'd expect the loads to reduce further as the target responds, moves away before the point of impact, and therefore has a reduced relative velocity. And that's still to test. So there's a wet version of that test rig being developed, and potential for passing that onto turbines at 1.2 metre diameter turbines, perhaps at a later date when we've quantified the forces and established that they're within the ranges that the instrumentation can tolerate. Okay, so that was a relatively quick fly through, but hopefully of some interest. Broadly, we've got a number of models that we've been developing for in-array loading, focusing on turbulence and wave loading. SPH further developed with this lattice spring method to model elastic bodies responding to impact with rigid bodies when in water. Validation methods being developed for that, and some validation data available for dry impact, but more work to be done. Okay, thank you very much.
Okay, we're being bang on time.
Okay, thanks.
Stay here.
Okay.
Some questions. I think this is exactly what this workshop's about. It's the activities where ecological questions interact with engineering questions. And I've worked on cetaceans for 25 years, never heard them described as deformable targets, but I do like that. Or clouds of, what was it? Cloud of points, cloud of particles, lattice of springs. I'm going to use that next time. I guess the point is, from an engineering perspective, you're putting a tidal turbine in the sea and a large megafaunal kind of animal comes along and strikes your turbine. What are the consequences for the gearbox, for the blades, all of that other stuff? And then exactly there's the inverse of that question is, what are the consequences for the animal in terms of consenting, all those issues? Is a strike going to kill an animal? And yet the modelling is exactly useful between those two questions, which are useful in very different spheres. And it's the conversations that go on between engineers and ecologists is exactly what today's all about. So with that, questions?
When you're representing an animal as points of a point cloud with different properties, do we know anything about how the force when it moves through tissue, whether it's going to damage that tissue or not? And could you have the cloud representing tissue of, for example, the lungs or the kidneys, and then represent it in that way so you could see whether or not there's likely to be a mortality event or an injury?
Potentially. It's a resolution question as much as anything. I don't have the numbers for how many particles are in those. I know that the first real whale simulation that was done there was one of the largest simulations they've done with this method. It had tens of millions, probably hundreds of millions of points. But in principle, any of the green points can have a different set of properties.
Yeah.
And as long as you've defined what the geometry of those points are relative to each other and what the stiffness is relative to the other nodes, then different characteristics can be represented. Yes. At the moment, there's no difference between each point along the spine, for example, but you could have flexures along the spine, for example. So that's doable. And on your other point, in terms of sort of damage, well, it hasn't been done here, but the properties can evolve with time. I mean, they do with the fluid particles, so there's no reason why the material properties can't change either. And there's been some related work using this method for modelling of cutting and modelling of sediment pickup.
Yeah.
So that's kind of similar in that you're quantifying the stresses in the material and then changing its properties as a result of those stresses. So yes, those things are doable, but they're developments of the methods rather than kind of established things in the method.
I'm sure Bernie was going to put his hand up, and he has.
Well, I didn't want to disappoint you, mate. I'm curious to your comments on whether this impact could be detectable by strain gauges, etc., fitted to a turbine, because this question always evokes a lot of emotion from various people. So I suppose the question is for that size of whale and the various turbulence, etc. That's the answer.
Not known yet, I don't think. I mean, we've got a reasonable understanding now of what the spectrum of loads is on blades in a turbulent flow. So I think it would be a case of that there would need to be some analysis of what magnitude of this shape of signal is detectable relative to that background turbulent load. And the turbulent fluctuations on the blade load are quite large, and some of them look a similar shape to these impacts. So I'm not sure that that is directly separatable at the moment with the instrumentation that we're aware of on blades, at least. However, that's on blade instrumentation that wasn't necessarily designed for picking out that kind of signal. We've looked at loading data from a full-scale turbine, which is what I'm referring to there, where there is large-scale turbulence. The idea of the tank test was to get some baseline data on turbulent loads so that we could subsequently pass these impact type loads onto it to see if we can detect that. So I think it's likely, if the impact loads are of the magnitude as we're seeing with the rigid body and the skin, but with the impact on a softer target, particularly if it's then got a reduced relative velocity, perhaps not. But to be investigated.
But this is so important. Yeah. This is so important for post-consent monitoring and all these other issues.
Yeah.
There's a question.
Just to follow on that, is the situation around individual turbines similar enough that you can filter on the basis of, assuming they're not all getting impacted by a school at the same time, would you be able to take away the signal?
Possibly, but I think that would only be analogous to taking away the signal for a statistically similar flow previously, because otherwise it would depend on its location within the site, if it's an adjacent turbine, a downstream turbine. So I suspect that there's things that can be done with that, but we need a set of data without and with to establish whether that is the case, and then look at which signals can be filtered out. I mean, I guess, you know, it doesn't even need to be an impact straight off, does it? It could be a case of looking at load data, superimposing one of these signals, and see if you can re-obtain or re-identify the signal that does contain that spike.
Okay.
Yeah, go ahead. So you said that with existing strain gauges or whatever sensors are on maybe production platforms may not be capable of detecting such impacts. But we have an opportunity now on the first turbine to go in Scottish water, should be in 6 months' time. Now's the time to think, well, what sort of instrumentation is needed over and above the operational instrumentation needed for the engineers to test? And do you have some ideas of what could be instrumented on this first batch of turbines, as I said, which might be identified?
Well, I think the main thing on that we'd identified from the sort of prior, the dry impact test prior to doing tank tests, is that most of the instrumentation on full-scale turbines or on turbines previously has been just hub instrumentation, so root bending. So you've already got all of your unsteady loads along the length of the blade, a lot of messy hydrodynamics along the length of the blade route, which you've got to filter back out. So the impact tests that we've done, we were measuring the root bending on the arm, but the plots that I showed are the point force at the tip. So I guess the key thing is, can we measure closer to the point at which we expect the maximum impact? So if we can have something that's located closer to the tip, then that's advantageous, but I'm not sure any developers are going to like it for that. It's quite hard to get instrumentation down.
So we're working with sensors across the road.
I was going to say, is anybody from sensors here?
So we're working with sensors who are one of the innovation centres across the road on looking at the different opportunities for sensors measuring strain on things. So we're starting to do that feasibility study at this stage, but yeah, absolutely, there's opportunities there.
But this is
just remind speakers, please, to repeat the questions for benefit of the online audience.
Sorry. I won't go back through all those at this stage.
So effectively, for that review, then this is the raw materials that could go into that review.
Yes, so the one we look at is, looking at what kinds of sensors and how do you attach them, because there's different materials and blades, and historically for wind turbines, it's always been an issue. How do you embed them? How do you get them to stay on? How do you put them in without affecting the properties of the blade from an engineering perspective? So it's starting to do that work. It's important. It's important for a lot of reasons, both from an environmental impact, but also from an engineering impact. You don't understand engineering that well either. So there's a lot to learn.
Good.
Sorry, yeah, just maybe even almost a silly question, but how does, or from your perspective, how does a marine mammal or a soft point cloud body, whatever, how does that compare with something more solid? So some other sort of degree, is this from a turbine perspective? How does that compare to something more solid? And actually, should the engineers be more worried about solid things impacting their turbine blades?
Yeah, fair point. So the question there was, how do the whales that are potentially deformable compare to solid debris that might be in the flow? And so I think one of the things that we looked at early on was this hard target compared to a target with a smoother surface target body, whatever. So the hard body there could be construed as anything that's like a container or some floating debris of that sort. And that's worst case basically. So impact with something that's hard gives from these experiments more than an order of magnitude greater force than something that's deformable. And that's, in both cases, neglecting the motion of that before the point of impact, which still needs to be accounted for, and you might expect something with sharp edges maybe not to move out of the way as fast as something that's rounded. So still to be quantified, but hard things, debris, worst case. That's fairly guaranteed.
I think in the original part of the project we're sort of scoping for things that would not be guaranteed to destroy the turbine, or things that would be so small to be trivial for the engineering, for things that would be sort of in the middle ground, so we sort of hit on basking sharks and minke whales. Okay, so we've got time for 2 more questions.
What's the possibility of using something like flowback to monitor objects that might be hitting the turbine? So as a kind of early warning response. So would you be able to put the brakes on a turbine to minimise the impact on the turbine blades, for example?
Very good point. So,
or minimise the impact on a marine mammal?
So question there was, can we use the turbine control system to minimise the loads? And I think, yes, very much so. These simulations are imposed rotational speed. And in fact, a lot of CFD and numerical models of turbines tend to be imposed rotational speed, which is a bit of a limitation. You can mitigate the unsteady loads due to waves and due to turbulence with the control strategy on the turbine. So you can that's certainly something to explore. And that might be one of the reasons why on larger scale machines it would also be influencing the instrumentation used, I expect, because you might need to know a bit about what the control strategy of the turbine is to actually know what your loads are on the blades as a result of the control strategy.
Okay. Last question.
It's not necessarily a question, but more a comment. Some of us were at NewTech a few weeks ago, and there was this girl called Molly Greer who kind of gathered dead bodies of orcas and different seals and things, and was looking at tensile strength, and she was stretching the blubber and pressing the blubber, and she's got real numbers that you may be able to input into your model. So Molly Greer.
Molly Greer. She's already got ethics approval, I think.
As long as they're dead, it's fine.
You could contact her.
Okay.
Thanks very much.
Good, that was good. And we are bang on time. I see a lot of interested faces. Only one laptop open, but that's fair enough. So not much email going on, so that's perfect. Thank you very much, Tim.
Good. Okay, thanks all.
Right, the next session we've got, the next part we've got 3 quickfire talks, 2 by imposters, 1 by the real deal person as on the program. And for the first talk, it's going to be not Simon Cheeseman, it's going to be Andy McDonald, who's going to come and talk from the catapult, and I need to find your slides.
Just the next slide.
Next slide.
They're all in the room.
Talk about organised. Okay, so Andrew's going to talk about innovation challenges. Is that what you want?
Yeah, it's got a bit funny, but we'll be all right, I'm sure. So hi, I'm Andy McDonald. I'm a Senior Innovation Manager at the Offshore Renewable Energy Catapult. So we're based literally 50 yards across the road in the building here. So I guess where's Tim gone? He's disappeared off. But I don't claim to be a real engineer, and I also don't claim to be a real scientist. So I guess I'm the cabaret act that Beth was talking about, just to fill in. But what I want to talk about is my background is electrical engineering. I worked in the South Violet tidal project, so I have experience of going through the consent process for a tidal project. My role within the Catapult is more about looking at commercialization opportunities for technology. So from your perspective, I absolutely value all the work that you do. It's very, very important. Keep it up. My perspective is looking to find opportunities for taking some of the research and seeing how we can commercialize it. So it's working in that space between research organisations and industry to see how we can actually add benefit to the UK. How do I put this forward? Is it as simple as it looks? I've got a wee bit wonky, these slides. They look beautiful when I put them together. So the Catapults were a network of innovation centres funded by the UK government through BIS. We're one of 7. There's going to be a couple more coming up in the next couple of years. Our aim is to bridge that gap between research and industry. We get a third of our funding from government. We need to get the other 2/3 in from elsewhere, so that's either joint industry programmes or other funding, other competitively won funding. Our key drivers are UK benefits. It's about impact. So anytime you're looking for impact, come and speak to us. But if you want us to help identify how your research can be targeted in the industry, and if you're looking for data to go into your research, again, more than happy to help with that. We're keen to see real impact from all the research that's going on in the sector. The other one is about cost of energy. We're driven heavily by reducing cost of energy, both offshore wind and wave and tidal. Those are the key things that really drive us from a practical sense at the moment. I'll go through this quite quickly. I've just got 5 minutes, don't I?
Yeah, you've got 2 minutes.
72 slides. It's going to be pushing it a bit. So we've got a centre in Glasgow. We've got 40 people over here, and we've got 70 people down in Blyth in the north of England. We've got fantastic test facilities. We've got some great engineers, fantastic test facilities, and I'll just whiz through the ones that might be of interest. This is the high voltage electrical, and I guess if you're looking at EMF, that side of things in terms of interaction with with any environmental targets. I'm not sure that's the right word, targets. But if you're looking at putting cables in docks in water and measuring EMF, we've got equipment that can produce high voltage and can recreate conditions. We've got a met mast out at sea, 3 kilometres offshore at Blyth. So you can do a lot of stuff there. We're doing a project correlating satellite data with ocean colour measurements. So we're putting equipment on the met mast, looking at the sea, and then correlating that with satellite data. We're doing a lot of work with the Satellite Applications Catapult, because there's a lot of good work relating measurements, which are point measurements, land-based measurements, with the wider spatial variation that you get using satellite equipment. I'll spin through this quickly. This is just the dock site, so we've got space to put things in the water. Come and speak to us if you want to use that. This is our newest asset. I don't know if any you've probably seen this if you've been anywhere in Fife, because it's 196 metres to the tip. But it's just from an offshore wind perspective, just to remind you of the scale of these things. They're very, very big. So this is at Livermouth near Methil in Fife. We now own it. It's the Samsung turbine. So it's kind of state-of-the-art technology. But from a research perspective, it's there as a research asset. So if you want to get real measurements, if you want to test LiDAR, if you want to look at impact, it is in the water. So if you're looking at testing paints, coatings, biofouling, we can facilitate that on this site if you're looking for real examples where you can test stuff. This is just me checking that I'm doing the right thing. So when we're looking at what the environmental impacts are, from our perspective, we use Ocean. I think we've done a fantastic job putting together a very clear list of research activities that need to be done for the sector. Tell me if I'm wrong. I should be using another list, but I think it's a very good way of classifying research needs to be done. This is kind of the crux of what I wanted to talk about. So in terms of what we're trying to do, it's about commercialization of technology. We kind of do it through two methods. Firstly, we put together more general technology areas or innovation challenges, which we put on our website, and we kind of garner interest from those, and we can provide a couple of days support to people coming up with new technology and say, is this right? Is there a market for this? Does it look right? Do some technical due diligence on that. If there's enough interest around things, we can then gather industry around it to try and put some funds together and do a call for particular innovation challenges. So the kinds of challenges, the kinds of things that are in Audit, our focus is much more about the technology than the environmental side, but the value of it is huge. So any delays to an offshore wind farm or to a tidal project, it's millions of pounds a day for every day that something is not up and running. And there's 2 offshore wind sites around Scotland which are now in the judicial review, around bird monitoring, that side of things. So the impacts of getting consent are massive. So keep working on it, please. These are some of the things that we have been doing. So biofouling, am I going through?
You're kind of going to, I'm just going to give you a cheap
Right, so we'll just go very quickly. Biofouling for open sea hydraulics. So what's the impacts if you're using seawater for your hydraulic system? Standards are important. We'll keep coming back to that again. The supply chain need to understand what standards are in order to develop products to fit in with that. The project with SAMS, I will let Adrian talk about that.
Okay.
We talked about the work we're doing with Census on looking at strain gauge type technology to really understand what impacts are for collision detection on tidal blades. Hydrock is the ocean colour, we looked at before. This was interesting. We did a report with Fugro. We found 70 data sets that were needed to gain consent. It's a massive amount of data. These are, this isn't just point data, this is large spatial data, bathymetry, geotech, geophys, environmental fish. It's the whole piece, but there's 70 data sets that are needed, so it's a massive amount, and those all need standards to go around. I think I'm just about finished. So future stuff, a few things just to throw in. We're looking at piling noise is going to be a big challenge for offshore wind. Monopiles are getting bigger and bigger and bigger. The regulations will get tighter and tighter and tighter. They're tighter in Germany. It'll come to the UK. We need to come up with practical solutions for reducing the noise impact. Bird monitoring we've talked about. We're looking at a project around tagging gulls, working with SSC on that. I can't remember who the other partners are, but I can find out if you're interested. Cable stability monitoring. We're working with TeraWatt on possible looking at cable prognosis, how cables move in tidal flows. Corrosion, scout protection are other ones which are very topical. I think that's me.
Thank you very much. So if you've got questions, hold them. I'll have the next 2 talks and then we'll come back and do a discussion from there. So our next speaker is the real deal, as on the programme, and it's Stephen Benjamins, and he's not. He's Benjamin Williamson, and there's too many Benjamins around us, as we know. And he's from the University of Aberdeen, and he's going to talk about wake effects of tidal turbines on fish behaviour.
Thank you, Ben. So thanks for the really interesting talks so far. I look forward to some good discussions today. This is just a very brief example of engineering impacting ecology, and then maybe how we can try and go full circle and use some of what we're learning about the ecology to then inform the engineering. So the example we're using here is using the flowback platform that you see at the bottom right-hand side to look at the hydrodynamics around tidal turbine structures and then how that affects fish schools and fish behaviour. So the platform gives us a tool to gather multi-beam data in the wake of turbine structures or upstream of turbine structures. We're using the multi-beam for target tracking and the vertical and horizontal distribution and the movement of targets in the water column. So here the colour shows the target tracked on this approach to the open hydro turbine structure at EMAC. We deploy the platform for 2 weeks at a time to get movement over a full tidal cycle. And we synchronize the behavioral data from a vertical multibeam with a multi-frequency echo sounder that then gives us a quantitative measure of the same targets when we link the two together and co-register the information. So on the right-hand side now, we're looking at a 2-week deployment at the wave energy site at EMAC, and we're tracking diving seabirds feeding on a school of fish at the surface. So predator-prey interactions, but also gathering concurrent hydrodynamic measurements from sensors on board the flowback platform. So this gives you just an idea of the kind of targets we can pick up. Different schools of fish, different aggregations, we can track their movements, their behavior, school morphology, how densely they're packed, how they're moving, how they're responding to the structures on the seabed. So schools of fish on the left-hand side, on the right-hand side, single solitary fish, diving seabirds at the bottom right. And so this hopefully will show. Okay, so this is just an example of some of the target tracking we're seeing. So closest to the screen, we're seeing this long track of a diving seabird. This is around the Atlantis tidal turbine structure at EMAC. The triangle shows you the multi-beam swath. So the frame is deployed here. This rectangle here is to scale the tidal turbine piling, the central piling. And we're tracking a variety of targets throughout the water column over a 2-week period. So we've got a 10-hour exert here. So what's really exciting is how we can use this data to build up a picture of what the fish are doing. So now we're going to compare a controlled deployment. So it's a back-to-back deployment with a deployment next to a turbine structure. So comparable hydrodynamic conditions, a comparable location, back-to-back in time. And what we're looking at on the right-hand side here is the vertical distribution of schools of fish over a 2-week period. So on the x-axis down here, we're looking at the tidal flow in one direction, up to about 3 meters per second, and then the tidal flow in the other direction, so the ebb and the flood. And looking at vertically, this pattern of, in one direction, even at some of the fastest flows, the fish schools are high in the water column, close to the sea surface. In the other direction, much, much lower down, towards the seabed. So what's really exciting is when we compare this pattern to a back-to-back deployment next to the Atlantis turbine structure. So in this direction, the flow, I'm not sure if you can see my pointer on the screen, I'm sorry. So on the right-hand side here, we're looking at the flow to the turbine. So from the flowback frame to the turbine, and over here from the flowback frame in the same direction. And we see the same pattern as the flow speed increases, the fish schools move lower in the water column. But what's really exciting is when the flowback platform's in the wake of the turbine structure, over here, we have this completely different pattern. Fish schools much lower in the water column, aggregating potentially around the turbine structure, potentially sheltering in the wake. So the work of the group at Aberdeen is looking at some of the hydrodynamic reasoning for this. We're gathering data from the flowback platform using an ADV for previous deployments, an ADCP for future deployments, and we see comparable hydrodynamic conditions. So we're looking at the back-to-back deployments again. We see comparable velocities. As we expect, there's a velocity deficit when the flowback platform is in the wake of the turbine structure. So that's the pink period on the left-hand side. But what's really exciting is from the work of our PhD student, Sean Fraser, who's saying that the turbulent kinetic energy is consistently higher in the wake, despite the reduced velocity. And what we think is this is a completely different flow structure, and this is what the fish are responding to. So potentially a fish aggregating device, potentially a fish sheltering behind it, responding to this hydrodynamics. And so what this means is that we have changes in fish school behavior due to the structure, due to the hydrodynamic effects, potentially altering the collision risk, first of all of the fish, but also the predators as well, so birds and marine mammals. Potentially changing the predator foraging location or efficiency around single devices and then around arrays of devices. And what that means, so we have the engineering impacting the ecology, but then can we take some of what we're learning about the ecology and come back around and inform the engineering of these tidal turbine arrays. And so that's what we're really excited about now, taking this forward with Mayjan, looking at operational tidal turbine wakes and array effects. Thank you.
Good, thank you very much.
very much. Right, our final speaker in this wee session is Carol Sparling, who's had a haircut and turned into Gordon Hasty. And it's a rather long title, so I'm going to read it out. Or is it still the same title?
I don't know, actually. What's the title?
Oh, it's shortened. Okay, issues at the interface between engineering and ecology, marine mammals and tidal turbines.
Thanks very much, Ben. It's very exciting, as it's going to be as big a surprise to me as it is to you what the next slide's going to be. Yeah, so Carol, apologises for not being here. I'll try and fill in some way through these slides. I think the two things that Carol really wanted to talk about were firstly, and it's great we're having this workshop because it's exactly these points. Firstly, how the integration of some of these monitoring devices really requires the very early engagement between engineers and ecologists to come up with a successful monitoring strategy, particularly for marine mammals. And I wanted to highlight a collaboration that's been going on between Tidal Energy Limited and the CMAP Research Unit as an example of where this has worked. And secondly, I wanted to raise, again, we've heard a little bit already, some of the potential engineering solutions that we could come up with in terms of reducing some of the impacts on marine mammals, such as rotor shape and rotor speed. And I'll highlight one study that's going on at SMRU that's kind of addressing that. Now, it's clear that the first turbines that are going in the water are going to require a reasonably high level of monitoring in terms of the behaviour of marine mammals around some of these tidal turbines, particularly designed to look at to give us an understanding of the potential collision risk in terms of the rotors and the marine mammals. And this is a study that we've been working on the Scottish Government Demonstration Strategy Project, which has a lot of parallels with this TEL SMRU collaboration that we're doing down in Ramsey Sound in Wales, where we've looked at a number of instruments, a number of tools to allow us to look at the fine-scale behaviour of marine mammals around turbines. Benjamin has already introduced the active sonar aspect of looking at the movements of animals around some of these turbines, but also using passive acoustic monitoring, so a range of hydrophones to track some of these vocally active species, such as porpoises or dolphins. But it's clear that some of these instruments have relatively high power consumption, relatively high data rates. So the ideal for running these systems is either a cabled solution directly back to the turbine or directly to shore. And it's clear that as we're integrating into some of these turbine interfaces, we're going to have it's going to be very important to have early engagement between the engineers working on the tidal turbine and the ecologists working on some of those environmental monitoring strategies. And this is the solution that Tidal Energy Limited and SMRU have come up with in terms of monitoring around their turbine. This is quite an unusual turbine. It's got a large triangular base. I think the original idea was to have nacelles on each of the three corners here, but ultimately, due to whatever constraints, they went for a single turbine in the corner here. And the environmental monitoring instruments that they've come up with are active sonar, which can be deployed on this remote platform off to the side. They call it the remote acoustic monitoring platform. And this also has multimedia ADCP in it. We also have a series of tetrahedrons of hydrophones on the base of the turbine here, which allow us to, or potentially allow us to track individual animals as they move past here. There's also a series of, as we already heard this morning, a series of different instruments that are designed to actually look for impacts between animals and turbine rotors. And these include accelerometers and strain gauges. And I guess one of the discussions that's going on is do these instruments actually work, and what instruments should we be looking at to detect collisions. This is a schematic up here of the data flows in this system between the environmental monitoring systems, the industrial plant sensors, so that the sensors are actually look at the operation of the tidal turbine, and this SCADA system ultimately feeding through to cloud storage for all the data stored. This is a photograph of one of the hydrophone tetrahedrons on the turbine. So you can see that it's quite it's not sort of thing you can tack on at the end of it. It's something that actually actively integrated into the turbine design at an early stage. And this is a photograph of the ramp, which is the platform that's off to the side. It has a multi-beam sonar in this little window here. There's a pan and tilt that hangs down here that you can control this, and it has your ADCP up here. And as I understand it, this was actually built by the engineering team at TEL from offcuts from the turbine once they built it. And this, I think, is designed to show how complicated the system is, certainly to an ecologist anyway. And probably shows us why us as ecologists probably should be getting into the actual integration of some of these systems into the turbine control. So the conclusions from this part are that first of all, integrating some of these scientific sensors with the plant control isn't straightforward. It's been quite a complicated process with TEL. And one of the things that really benefited from it in the TEL system was being able to plan that system architecture, including all the environmental systems right from the start. And it was a real advantage to putting together this environmental system. And also it's clear that both wet and dry testing is fundamental to making sure these systems work, both on the dock side and once it's in the water. And the last part, I think, was feeding on from some of the work that Tim and Ben have been doing. How might we change the engineering design of some of these turbines to potentially reduce the impacts on marine mammals, potentially reduce the impacts on ecology, and as Benjamin said, using that ecological information to feed back into the engineering design. And certainly some of the work that's being carried out at the CMAM Research Unit, in a very similar way to Tim, we've been looking at the potential effects of collisions with animals. But the approach that's been taken there is actually use real animals, so carcasses of dead animals, and actually hitting them with a simulated blade profile at the kind of speeds we're anticipating these rotors will be going at. I'm looking for things like skeletal damage before and after these impacts. And Dave Thompson and Joe Onufro have been doing that part of the project. And it's clear that from some of this work, it looks like, as we might expect, alterations in rotor speed might have a significant impact on reducing some of those, or some of the consequences of those collisions. But also some of the stuff that's coming out is quite interesting, that is looking at the actual shape of the rotor. It does seem to have an impact as well. Maybe what we should be looking at is a curved tip to the rotor rather than a straight edge. And it's these kind of discussions, I think, that us as ecologists should be having with engineers at a very early stage. It may not be feasible from an engineering perspective, but at least if we have those discussions, we can either rule them out or push them through. Oh, thank you very much. That's it.
If the speakers could come up. Right, now you can unleash your questions. Yeah. Okay. Rhea.
Is there, with just thinking about the things, the ways that you could change turbine operation to reduce impacts, things like changing your rotor speed and the shape of the rotor. Making changes like that, is there potential that could actually make tidal energy unviable? So for example, if you slow your rotor speed, perhaps you might produce less energy, which means that your returns are less. Is there a chance of that, or is that change potentially so small that it doesn't really matter?
Someone restate the question for the mic.
So the question was, do changes in the rotor speed potentially cause such an impact in terms of the finances of the project that makes it unviable?
Yeah, pretty much.
My personal thoughts would be potentially yes, and I think that at the moment the costs of tidal energy are far higher than they need to be to make them even with the current subsidy regime at the moment of £305 per hour. We're still 60% over what the cost would need to be to make that a viable project. So, which is why projects haven't gone ahead. So the Sound Violet project was consented in 2011. So there's nothing happening because it's not an investable project at the moment. So the margins are just not there. The cost of energy is currently too high. Now that's not to say that in the future we shouldn't be looking at that, because I think the other side of it is that if you can't make it environmentally acceptable, then there is no industry anyhow. So we do need to balance that. But I think that if you're changing a design and knocking 5% off the aerodynamic performance, I think that has a huge impact on the economic case.
So my question then is are we preemptively thinking about these sorts of changes too soon before we know that there's actually an effect?
I think we should think about them, because I think that, this research takes a long time, and you need to start looking at it, and I wouldn't rule anything out. I certainly wouldn't be saying that, but I think that in practical terms, what you're more likely to do is to put your site where there's less chance of collision. You're more likely to do it by positioning it in a different site, and therefore the understanding of where mammals and fish are, and what their behaviour, the changes are, and the displacement implications are, equally important in terms of actually, reducing collision risk chances. That's my view.
Can I say, I reiterate that fully. I think the important thing is we have these discussions, I guess. I, as an ecologist, don't have any idea about what the reductions in efficiency by changing some of these parameters are. But I think we need to have those conversations. And if there's a choice between a slight reduction or not getting consent for whatever mammal reason, I think that's where these things become valuable.
I was going to say one thing, and then come to Imogen, was the animals colliding with turbines, whether they're fish or marine mammals or birds. At the moment, it's a risk, a concern. Whether it's true or not is mostly a result of how the animals behave around the turbines. We know that if they don't behave, they will negatively interact at a significant rate. But it's how they behave, and we're only going to find it out by actually putting real turbines in the sea. There's only so much you can do in a fish tank. So the way it's going is correct in saying that the industry is putting some turbines imminently in the sea, but we've got to monitor them to understand whether there is an issue or not. We've got to have, hence the whole understanding of whether we can actually detect a strike. Before burning up, Adrian.
Question for Benjamin. Really interesting talk where you see the wake effects of and the fish sort of responding to that. I'm just trying to think how I might use that in a kind of environmental impact assessment point of view. And we're looking at sort of population scale impacts on different species, whether it's commercial fish species or migratory salmon and these types of things. So it's just the question is. Really useful data to know that. It's just I wonder how we use that in a practical sense to inform regulators, to inform people trying to make decisions on whether these things should go in the water or not.
Yes, yeah. So for changes in the fish behaviour, certainly we're beginning to understand a little bit about what we're doing, whether we're aggregating fish, whether we're creating habitat, whether we're changing habitat. I think, and probably Beth will agree as well, we need to know what that knocks onto. So how does it change the behaviour of the predators as well? And then using all of that. And then as well, rather than just around a turbine structure, but around an operational turbine, what changes there? Is it just the structure in the water? Is it the hydrodynamics?
Yeah.
Is it the presence of the structure? Yeah. I don't know, Beth, do you want to add anything to it?
I would add, the first thing we can do is put it into some models, especially behavioral models. So we do have another person, Marianne Gimanti, at our university, looking at diving bird behavior and looking at the difference between birds that can catch one or multiple fish and what it means to have an aggregated, predictable bunch of fish in a location. And that works quite exciting to show there's quite big differences between multiple loaders, single loaders, and that for some of them their efficiency has actually got an optimum. That if the fish are predictable within a set number of turbines, their efficiency goes up. But actually, if you put too many turbines, the same number of fish can hide behind lots of turbines, their efficiency goes down. So it's incredibly complicated, but the first thing to do with this data, absolutely, I think, draw these kinds of models and then use those individual-based models up to population levels and see what the differences are.
Okay, from Ms. Bernie, do you want to
Happy to.
I've got a really quick question.
I'll still burning up later, right? Go ahead.
Is that kind of information transferable between turbine types? So is it purely based on the reduction in velocity because of flow, which you would expect, similar for open hydro as for TEL, as for Atlantis, or do you think there's anything turbine specific going on?
I think as industry starts to converge on common designs, even if not identical designs, then we'll start to see similar changes in the hydrodynamics, and maybe Tim might add a bit to that. I think what will be really interesting to see is whether it's site-specific. So even if you have the same turbines, but in new sites, animals in the site. Tim, what do you
Yes,
think?
absolutely. I mean, there is quite a difference between the wake of something like an open hydro and open-bladed turbine, some sort of three-bladed turbine or something like that. In terms of the deficit and in terms of the turbulence characteristics, really. So yes, in that sense. And I think not necessarily site-to-site variation, but even within site. I mean, the field data that we've seen suggests that the turbulence characteristics differ a lot at the same location at different points in the time, different points in the country. So I think, quantifying the turbulence levels that you get as a function of the machine and as a function of location of the bathymetry are quite important aspects.
And I guess the position in the water columns, that we're seeing a kind of second generation of turbines, the Scott Renewables turbine, the electricity turbine, which are higher in the water column or near the surface, and they're going to be affecting, I'm assuming, different species.
That will cut into EIA type considerations.
Well, that's sort of why I asked it, is are these others applicable to, say, consultants doing with the regulators sort of thing?
Well, one aspect of Ben, we're talking about predators and change of behaviour. In terms of setting up larger arrays, you would exclude human fishing activity from those arrays. And that, I'm assuming that would have an effect in terms of behaviour, particularly I think crabs and lobsters, and from that side of things rather than fish, which would be fishing in those sites anyhow. But there will be knock-on effects there, and certainly some of the kind of positive positions, I guess, put forward during consent to the Sound Bylaw was that it would actually improve conditions for crab and lobster by creating zones where they aren't being overfished. Let's just look into the other way. I guess there's human behaviour changes as well that go along with some of the development.
John, very simple question. Do you have any idea, Ben, what the species of fishes were that you were recording? I mean, you were recording some high up in the water column. Were they the same species that you're recording lower down in the demersal environment?
It's one of the things we're trying to look at. So we can get an idea of fish size from the echosander. We can look at fish species which are known to be in the site and then try and discriminate between them based on either their behaviour, their size, their schooling behaviour. But we haven't done any trawling, any ground truthing. So from the shore-based observers, we see the species the birds are picking out from the water and recovering. We've got some camera surveys in the sites that are proving to be very useful. And I think as we go forward at the major site, we'll be including cameras there as well. So gathering bits of information that we can.
So I think Open Hydro certainly had cameras on the device in Fort Warners.
Yeah.
And they were recording, I think, almost universal pollen around the device, which one suspects was some sort of reef effect. Whereas you seem to be suggesting almost different from a reef effect. It's a turbulent structure that's attracting a particular fish species.
Yeah.
And I'm wondering, because that occurs on both your control site and your test site where you have the turbine, whether that turbulent structure is also occurring naturally at the control site as well as in the wake of the turbine.
Mm-hmm. So by having the comparison between the ADV at the control site and the turbine site, we can start to tease apart the differences caused by being in the wake of the structure rather than just being a couple of 100 meters away. So we know the direction the flow is coming from. We know the period when the flowback frame is in the wake of the turbine structure. So we can start to see what are the differences from the turbine being there. In terms of using the camera data, really useful when you've got that visual range, you've got low enough stability and good enough natural illumination. For periods of night, periods when they're much higher up in the water column, we're having to resort to acoustics or knowledge of the species in the site.
That's a really interesting point, and I'm just wondering if, I was going to come to that, but if anybody's looked at the distribution of, say, gadoid fish, or whatever it might be, in relation to the turbulence associated from picked up with an ADCP or something like that. Go best.
Well, I have to say, the problem is a lot of ADCPs have a bit of software in them that throws out information about fish, because fish usually are going in the opposite direction to an ADCP. So there's software in there that calls that error and throws it out. One of our original plans was to look for fish from ADCP data. But my other point was, Benjamin didn't mention that the multi-frequency that we're using, the EK60, which is a very expensive machine in terms of just cost but power, but it does provide us with the different frequencies of fish. So fishes that are commercial, i.e. things like mackerel and cod, and herring, we can actually, from 20 years of fisheries data, look at the data and pick up what those different species are. So one of the pictures we have there, we're pretty sure the biggest school we've seen coming through is mackerel in that site. So, but as Benjamin correctly says, we have nothing to ground truth it other than looking at fish that birds are coming up with in their mouth.
Mackerel should be easy because they haven't got to swim in that, so it's a very distinct picture. You should
Everybody.
It's a question perhaps to the panel, perhaps to the wider audience. How well can we simulate the flow of water through either one turbine or an array of turbines? The reason I say this is because we'll be looking at the movement of marine mammals in the vicinity of a turbine as it enters the turbine blades, as it exits. And we'll be looking for behaviour which we hope the animal will exhibit to basically get the hell out of the turbine blades. But what's the null model? What would we expect, you know, like potatoes or something in the waterfall to behave? What's our null model? So my question is how sophisticated are our modelling techniques to predict what a particle of water would do, or a bag of water would do, as it approaches, as it goes through, as it exits, as it goes into the next turbine array. What's the state of the art?
The first, the early images with a turbulent flow approaching a turbine were quite a costly computation trying to represent the EMEC flow. That was run on EDF's supercomputer and took about a month to do 6 rotations of the turbine. So it depends on what resolution you want. To get something moving through turbulent structures, coherent turbulent structures in the flow, you need that kind of method because you need an onset turbulent flow. Otherwise, it's not deformed by the rotor plane. But so from short distance upstream to through the rotor plane to maybe a diameter or 2 downstream, that kind of approach is tractable, but we don't actually know how accurately it's predicting a packet of water. We just know that it's getting the loads quite well. So it's getting the loads quite well, it's probably getting the packets of water quite well. At a larger scale, at the array scale, turbulent modelling with coherent turbulence isn't really tractable yet. A few people have done approximate studies, and there's been some very costly simulations done that are analogous for wind turbines, but mostly the focus is on mean loads on the turbines rather than on the accuracy of turbulence parameters on the wake. So some parts of the wake we can predict quite well in terms of average characteristics, but certainly the near field, probably from a diameter to 3 diameters downstream, hard at the moment. I wouldn't have much confidence in that region.
Can I just follow on and say, is there something that we think would be useful to the community? When you say it takes a lot of computing resources, I acknowledge that it must be, yeah, it's going to be a lot of resources. Would this be some sort of useful tool that the community could share and get together with some proposal to whoever it is that runs these computing models?
Well, I think these kind of things are being developed. I mean, various groups are doing they're called actuator methods instead of blade resolve methods for turbines. But I think the focus traditionally has more been on the blade loading. Yeah. So I think it's really now a case of shifting that emphasis onto how accurately aspects of the flow field that are important for ecological reasons are predicted. And there's a growing field of people looking at that, but perhaps more again in terms of the unsteady loading of downstream turbines, where you do need to then know what the flow field is in an unsteady sense. So I think that's coming. I don't know what the kind of particular effort would need to be. I think there's some things developing that might address that gap, but there's certainly a need for understanding what parameters are important for this type of work, for this ecological.
So this might be something that we might consider later on, just to see if this is a useful tool where I think it's important. Yes, you're doing this from the engineering point of view, the effect on blades is understandable, but we maybe could consider later on whether such developments, including dynamic modelling, would be worth pursuing.
Tim, can I, from your perspective, you're obviously doing the modelling side, are you finding that you're getting enough real data in order to correlate what you're doing in terms of the modelling side? Because obviously when you rely on ADCPs, there are limitations of ADCPs in terms of some of the sites. I'd love someone to come up with some better than ADCP. We've spoken about, can we, for offshore wind, we've moved from cup anemometry to LiDAR, and that's produced a lot of very, very interesting research around wake effects, and I want to see the same change in the marine side. I was wondering from your perspective, and I guess anyone else, is there a shortage of data? Is there something we as a community can do? Because there are sets of data collected from a number of sites, but they're not generally pulled together and available. Is there something that we, speaking from the catalogue, can do to kind of help to broker those data sets?
Potentially, I mean, we've been relatively fortunate in having access to data through this ETI REDAP project, which has had quite a lot of monitoring from the turbine and around the turbine at the UMEX site. But that has flagged up some issues with instrumentation. There are parameters that, if they are important, some of which are important for loading, are very hard to measure. I mean, the length scales of the turbulence are very, very important for loads, and yet virtually impossible to get from an ABC figure. So there's needs for instrumentation, but on the other point about how the data could perhaps better be used, but I think there are some cross comparisons between locations. But yeah, I think having more general access for this community and for the kind of load modelling community, if you will, it would certainly be useful rather than saying, we're representing site X just because it's got published documented data. So I think perhaps the most valuable thing there is a set of well-defined representative cases in the first instance for modelling. What cases do we want to know? Can we accurately predict the flow field for this compared to full-scale field data? So even just a study of which are the most documented cases to then be able to analyse loads as well as flow fields, for example, would be perhaps a useful exercise.
I've got a point.
And your impacts that you talked about, they're quite sort of small area in the sense of focusing around the turbine. And I was just wondering if any of you are studying sort of the more indirect impacts, in the sense, for example, I'm thinking that the turbines might affect the sediment, and the sediment therefore might affect ecology. I'm thinking that the turbines, depending on the size of the array, if it's a tidal one, might actually change the tide, and it might reduce the tide, and if it reduces the tides, then what impact that can have then on ecology as well.
Are we going to get into that after the coffee break?
All right.
That's kind of where we're going, yeah.
Hold on, that's this afternoon.
Okay.
Just to respond to the data query, again, this is what you see this afternoon. We're looking at much wider scale, regional scale stuff, and one of the biggest limitations we face is lack of publicly available data. Looking at the example of Penn Firth, all of the developers who've got options or sites around there have done their own HCP surveys, but the majority of them won't share them with anybody. And so it makes it very hard to try and pull that data and actually validate these models.
Can I play devil's advocate a little bit and counter Bernie's point to say, ask, does it matter? Does it matter if we're showing a response compared to a null model? I mean, surely what matters is whether the animal goes through the turbine rotor and get hits, whatever the mechanism behind that. Does that matter?
Discuss.
Discuss it. Over to you.
I suppose the practical problem here, the applied problem of predicting how many animals will get hit, etc. I think if you're an animal behaviourist, and we must be careful here that what we're doing isn't just for doing high-quality animal behaviour work and all that sort of stuff. It is the massive practical problem. So,
But okay, I'm going to go in the opposite direction, because I think it is important if we're thinking about, most of what we talked about is a single turbine and an animal interacting with a single turbine, but we're going to have arrays of turbines. And what happens to animals as they go past a turbine, survive that one, no problem, wave as they go by, but then they end up in the wake field of that turbine, and then what state are they in when they approach the next one? And if you think about a school of fish, something like that, is the school upside down or mixed up? Or so in those respects, the kind of medium scale is important. I think the school of fish might be like a sack of potatoes, if you want to go there.
Could you, just to start understanding that, could you look at some of the work that's been done on
We're about to conduct the weekly fire test. Thank you for your forbearance. I repeat, we are about to conduct the weekly fire test. Thank you.
is the alarm involved?
No, set lights of the building.
Could you build on what happens to fish when they come out the other side of turbines from those experiments where they've fired fish through turbines already, and understanding how fish react to the turbulent flow behind a ducted turbine or something like that, it's much more easily modeled, that they understand a bit better, and then scale that up to existing turbines and use that as a starting point for that to work for arrays.
I think it's going to
Attention please, attention please. Fire has been reported in the building. Please leave the building immediately by the nearest exit. Do not use the lifts. Attention please, attention please. Fire has been reported in the building. Please leave the building immediately by the nearest exit. Do not use the lifts.
They only need to do that once. I'm sure that came out on the microphone.
Yeah.
More question?
Yeah, so there's been a lot of work done on shooting fish through turbines.
Right, okay.
And people have videoed it and looked at what the fish are like afterwards. So could, for example, whether or not the fish can cope with disorientation from turbulence or whatnot, is that a starting point for this sort of understanding what happens when a fish approaches turbine number 2?
I guess the question depends on whether the fish that they're firing through turbines, I seem to remember it being trout, something like that.
They've done it with a few different types of fish.
Okay, yeah, whether they're schooling fish or not, because there's a big difference in how an individual behaves and goes through, reacts to what it perceives versus a school who will be reacting to what they perceive and the individuals around them. And then that kind of opens up all the angles about predation, risk, and predators coming in and being trapped, and so on.
Can I add that very quickly, that we had a visitor from the University of Maine last week coming over, and they also have real data of fish going through turbines, rotating turbines.
That's what I was thinking about.
So I would come back to Andrew and the OJIT people in the room and say, what's the possibility of that kind of working together, being able to get North American data and collaborations across the oceans with people who have that kind of data.
I mean, thinking back a couple of years from I guess the EMO meeting where we discussed similar things, but we're an awful lot more focused now in the questions that we're starting to address.
That is a fire test complete for this week. Thank you for your time. Thank you.
Well, thank you.
Right. Deep breath, right.
I have a question comment about the data issue that we're talking about, developers not sharing data. Tim and I work for a project called CCAMS based in Wales, which is a project that works with developers or companies to support growth in the marine sector in the areas of Wales. It's EU funded, ERDF funding by the Welsh European Funding Office, and the condition is that all the data is then open source and freely available. Is there any kind of project that exists like that in Scotland? And we're quite early in terms of working in marine renewables. Does something like that exist?
I'm going to say two things. First, I'm going to say that in the decommissioning workshop yesterday, this came up, and there was nearly a punch-up. I think I had to quiet it down, where people were saying all the government data is freely available, and other people were saying, A, it's not available, or it's unusable. The other thing I was going to say was that projects funded by the research councils, for example, that data should be archived and available, and so I presume that's true for TeraWatt and others. But there's a big variation in it, and also in terms of quality control of that data, you can take all your data and then put it onto some server on the cloud or whatever it might be, but is it usable by other people today? Is all the other ancillary information with it, so you can unpick what it was that was done?
The idea that we're going to go with the CCAMS is that probably they can, the data will be available, that they can come to us and we can tweak it or explain to people how they might want to use it. And I suppose the difference with the Research Council grants compared to CCAMS is that we talk to developers and say, what is it that you need to help you get through the consenting process, for example. it's not consultancy work, it has to be research-based questions, but perhaps there aren't funds in place in some of the research grants that are purely academic, whereas ours are more applied research questions that are focusing on potential impacts or things that might hinder the progress of development. So they're very applied to the actual company. The company tells us what they need to help them with their growth, and then we come up with research questions.
I guess that's one of the points of this morning is that people look at the same data from all sorts of different angles as well. You've got it right here. It's the same bit of information, but how you look at that may be very different. So it's a challenge to make it robust to different modes of interaction.
And I'm not aware of anything, and I'm kind of keen to emancipate data. But my colleague Paul Ellsworth has just started working in Wales as a kind of regional representative, and I'll pass on his details, because I hear it from quite a number of sources that they're not getting it, but I kind of need to build up that evidence base to kind of push a project around that and just understand what data, and you're absolutely right, the data is no use without the metadata around it that describes it. So my personal experience is that a lot of the developers will share data, they just, it's a pain in the neck for them to do it, because they've got to go through their legal teams and they've got to go through all kinds of sign-offs to get things done, and they're just too busy. And actually, my suggestion would be, in terms of setting up some kind of brokerage, is you agree with them once what the limitations on that data use is, you agree with them what they want out of it, what is it for research purposes, do they need to be published, do they need to be named, and then you agree that once with them, and then when somebody wants it, they tick the boxes, and you can get that agreement done with them. But that's where I would like to see it go. It would be good to get some kind of working group together to actually look at that, or to actually just even get a group of people that are saying this is a big issue. And you look at last year, and there was so Palamas went into administration. There's a stack of data there. I mean, they have all of their data from real live real performance data. That's sitting on a hard disk through Edinburgh at the moment. We've in Scotland have that. I'm trying to encourage them to free that data, because I think that would be a big data set to get people focused on as well. So EMET likewise, I don't know if there's anyone from EMET here, but I'm encouraging them to free up their data as well, because they have a lot of data, and I think they see some commercial value in it. I suspect it's not. I suspect it's of more value pushing it out for research in an open source way. That's my personal view.
Just to add to that, the other source of data will be through environmental impact statements, and that's another one that is difficult to share, and this is one of the things we've been discussing at meetings at the International Station Impact Assessment. It would be great if data from the environmental impact statement was made general.
So the one place where it is stored is on the Marine Data Exchange, which is the Crown Estate's repository of data, and that's publicly accessible. It doesn't necessarily have everything there, because people can say it's commercially sensitive and not pushed on. But the Crown Estate are there. I think they're open to people saying to them, actually, for these sites which are no longer actively being worked, the Crown Estate have it within their rights to be able to ask people to publish that data. So there's an option there to, if the specific sites you're looking at or you'd like information on, it's working in discussion with the Crown Estate to see if that can be pushed out.
I mean, I think there is a slight difference between the type of data collected for an EIA compared to maybe a research question, especially at the moment. Some of the requirements for the EIA process maybe aren't focusing on some very specific impact-related questions.
Yeah.
So, from an ecological perspective.
Good. Last couple of questions.
And with the fish schools, some really nice patterns across different tidal states. I was wondering if those observations were maintained with night and day periods, because that can make a massive difference to behaviour, and also over kind of weekly to monthly periods of time. I can't remember how long the frame is there for.
Yeah, it's a good question. So the two graphs we showed of the vertical distribution are each the sum of the 2-week deployment, so the full New Spring tidal cycle, but compounded over day-night. So what the kind of concurrent analysis we're doing is how does that vary with day-night, Unfortunately, in terms of things like seasonal data, we've just got the 5 2-week data sets so far. So that's why with the major side, once we have cable instrumentation, it becomes really exciting to try and look at the seasonal distribution as well. So day-night's kind of in progress, and looking at some of the other covariates as well.
Anyone else? I think everybody wants a coffee. Now's the time for coffee. So first of all, would you thank me? Would you join me in thanking our splendid speakers? You've got half an hour for teas, coffees, biscuits, whatever it is. Please come back here for the second, the mirror image ecology impacting engineering session.
For the benefit of our online audience, I'm going to turn the microphone off. We'll be back at 11.
Come in and take your seats. We'll try to get started right on time. And Simon, you're trying to get back on? Thank you. So if there's anybody new that wasn't here this morning, please know that this is being recorded for webinars. So anything you say will be recorded and perpetuated.
All people listening online, please stay close to the microphone.
Okay, so now we've flipped around and we're looking at ecology impacting engineering. And again, as with the first session, there'll be one longer talk and then three shorter talks. There'll be time, hopefully, for a couple of questions after the first talk. And then after all of them, we'll open it up for questions and more discussion. So the first presentation will be from Adrian McLeod from SANS Research Services Limited. And off you go.
Thank you very much. Thanks, folks, for having me here to talk to you today. Yeah, I work for SANS, for the commercial side of SANS, and I work on a range of different projects to do with the impacts of renewable energy on the marine environment. I work on biosecurity. We do some work for statutory nature conservation bodies. I'm sort of jack of all trades, master of none, but today I'm going to be speaking to you about biofouling and hopefully give you a flavour of what biofouling is to different people. If this slide would just shift on. Seems to be jammed. There we go. Yeah, so what biofouling is to different people, how biofouling affects the engineering of marine structures, and for this I'm going to give a brief overview of some of the engineering concepts. There's one equation, I do apologise for it, and I'd like to state right now that I'm an ecologist, not an engineer. For the engineers in the room, I do apologise. And finally, I'd like to look at how ecologists can use information on biofouling to inform engineers to make better decisions, to optimise the performance of the device. This is very important in terms of making this a successful industry. So what is biofouling? Well, to engineers, biofouling is the accumulation of unwanted organic material on man-made structures. For ecologists, it's a biological community on hard epibenthic substrata. Biofouling information is useful for ecologists and engineers alike. For example, biofouling might be useful to inform stakeholders about non-native species. We're increasingly urbanising our marine environment. How does that affect the ecology on surrounding habitats and species? But from an engineering perspective, biofouling is this collection of animals. And this is a deep sea, a riser about 100 metres in the North Sea, an oil production riser, some work we were doing on that. So biofouling species tend to be predominantly filtered feeding animals, and they have these planktonic larval stages. This is important for considering where we're putting structures into the marine environment and when we're putting structures into the marine environment. And I think for the engineering side of things, I want to focus on two main problems. The first one I'm not going to dwell on. The second one I'm going to go into a bit more detail. First one is accelerated corrosion. Now, biofouling can increase the availability of hydrogen ions at the surface of structures and increase corrosion rates. It can also mechanically damage the protective coatings on structures. So this is an example of a navigation buoy where we're seeing pitting formed by barnacles, which is mechanical abrasion. Environmental loading, on the other hand, can be split into two main elements. The first one is added weight, so that's a static situation where we're increasing the weight on the structure, and dynamic loading, so hydrodynamic loading, and I'll go into a bit more detail on that. So increased weight, and it's important to note, and sorry for those of you at the back there, but the weight in water is equal to the weight of the biofouling minus the weight of displaced fluid. Now this is Bernoulli's principle, there's nothing new here, but this is really important when we're considering what types of species are growing on your structure. So if we have a kelp-dominated community, that's seaweed, we're going to have a similar weight in air to weight of displaced fluid. So you're going to have a low static weight working on that structure. This is different when we're considering barnacles, bivalves, more dense organisms. So that's the first point. The second point really is to look at the hydrodynamic loading. And for this, I'm going to try and make this very simple. Apologies to the engineers. But really we're talking about what type of flow there is. Is there a steady flow or a variable flow? So this is an example of an unsteady flow, a wave environment. But in the renewable energy perspective, on tidal energy turbines, we might be looking at steady flow. I'll come back to that point in just a second. So we're really talking about drag and added mass coefficient. And these come together in Morrison's equation, which we'll get to in just a second. But drag is very simple. Drag is the frictional force and the pressure differential. Okay, so these different objects have different flow characteristics around them, and therefore you'll have a different frictional force and a different pressure differential. And the drag coefficient on the right-hand side there shows how this is working. So how does biofouling affect that? Well, first of all, biofouling will increase the size of the structural element, but will also increase the roughness of the structural element. Okay, now rougher structures have thicker boundary layers, therefore greater frictional force, greater pressure differential. And we can look at how engineers view this data. So on the x-axis, apologies for folks at the back there, on the x-axis we have the relative roughness height, so that's the roughness minus the size of the structural element against the drag coefficient. And for macro fouling on a offshore riser, we're really operating at the top end of this graph here. For micro fouling on a turbine blade, we're more concerned about the bottom end of the graph. Okay, so moving on to added mass. Added mass it took me quite a long time to get my head around because I'm not good at these engineering type things. But added mass is basically the force required to accelerate a volume of fluid around the structure. And this diagram points out very nicely. We all know intuitively it's going to be harder to push the larger plate into the water. So that's the added mass component. One equation. Morrison's equation is what engineers use to estimate the force acting on their structure. And it's basically made from two components. This side of the equation here is the drag side of the equation. That side of the equation there is the added mass side of the equation. So in a situation on the right-hand side where you have unsteady flow, i.e. in the wavy environment, the added mass coefficient is more important. On the other side, where you have a more steady flow environment, the drag coefficient is more important. Okay, let's bring these concepts together and have a look at what engineers might be concerned about when they're developing their renewable energy structures. First question is, does the device do what it was designed to do? I.e., does it convert kinetic energy into electrical energy? And we might be interested in what's the buoyancy acting on a wave energy converter? What's the weight, the added weight on that wave energy converter? How does biofouling affect the blade efficiency? Also, what mechanical moving parts are very important for the functioning of that device, and how will biofouling affect the moving parts? We might take this further to ask the question, does the device have adequate support structures? Can it withstand the environmental loading? And I don't have to go into these. We know about structural weight already, the static weight, the added mass coefficient, and the drag coefficient. And biofouling affects all these things. And you could argue that the size of renewable energy devices relative to the biofouling that we see makes renewable energy devices perhaps slightly more sensitive to when compared to megastructures in the offshore oil and gas industry. So we as engineers, or I say engineers, should focus on optimizing the performance of the device to try and reduce cost, reduce maintenance cost, and that's why we're interested in how we deal with biofouling. So what information is available to these engineers? Well, they can actually make observations from similar structures within similar environmental conditions to explore what are the characteristics of biofouling, what's the weight, what's the roughness, what's the thickness. They might also survey their structure as biofouling starts to generate on it, and that might inform their decisions of whether or not they're going to undertake costly maintenance services. But most often than not, where biofouling is at, in an engineer's perspective, is using standard guidance and recommendations produced by people like the ISO standards or the DMV standards. I'm going to look at one of these just as an example just now. So if I'm an engineer, I'm trying to develop an offshore renewable energy device, a wave device, I need to look at the position mooring standard for that device. And this is what it says about marine growth. Apologies for the folks at the back again. But marine growth thickness is a function of how high it is in the North Sea, and that's the important part, it's in the North Sea, the latitude, and how deep this structure is going to be. And these are conservative estimates based on protecting lives, protecting property. If I want to measure the weight of that acting on that the mooring, I'll use a density estimate of 1,325 kilograms per meter cubed. That's roughly equates to mussel-dominated community. And my next slide will show why that isn't the case. So this is an offshore riser. This is some work we did in the North Sea. It's a huge structure, quite a slender structure. You can see the buoyancy modules here on the upper part of the flexible riser. And the community was dominated by a deep sea species called Chirona hammeri, very, very large species of barnacle. So we took this material and we estimated its density. And not only did we estimate density, we looked at the density of the different fouling components, the different species that are there. So when you have a Metridium-dominated community, we're working on much lower densities than these standard best guess scenarios. Again, this is reflected in the weight in water. And this type of information can be used to better inform engineers about the loading on their structure. So I'm just going to finish up because I realise I'm running out of time. I want to finish up with an example from some of my previous work looking at biofouling on offshore navigation buoys. And what I did here was I tried to target as many artificial structures in very high flow environments, also in very low flow environments, in areas that are being developed by renewable energy companies. So, you know, I visited Billia Crew, I visited the inner sound of Skye, as well as the sound of Isla, etc. And we looked at the percentage cover of different fouling groups, and we also looked in much more detail at the types of animals and plants that were present, as well as measuring the density and the volume of that material. And to summarise very quickly, biofouling communities are very different in different geographical areas under different conditions. Well, okay, what's new there? This is a point that needs to be stressed to engineers for them to optimise the performance of their device. And we have this information, this biological information is available. We know whether something is a mussel-dominated community or a kelp-dominated community. So why can't we use this information to produce better models? Looking at things in a bit more sort of a scientific manner, out of all the variables we looked at, deployment length, flow speed, salinity, temperature, one of the most important variables was geographical location. And we can see here that buoys in different geographical areas or different deployment zones were slightly different. Have you all come across this type of graph before? The points closer together are more similar communities, points further away are more dissimilar. So let's take this a step further and then look at the weight in water. So this is the weight in water in different geographical locations. And we can see here that Mytilus up here, that the mussel-dominated communities are the communities with the greatest weight in water. So we can start using information here about the biofouling community and inform engineers about the weight acting on their structure. So I've tried to take this a little step further by producing predictive tools. How do we use ROV footage, for example, to estimate things like the density of the biofouling? So this is data from the navigation buoys. And again, how do we use things like the proportion cover of hard fouling to estimate the weight in water? So, in summary, we've talked a little bit about what biofouling is to ecologists and engineers. We've looked at how engineers use this type of information and how ecologists might be able to improve on what we're calling best guess at the moment. And finally, we'd like to develop tools to help engineers to understand the loading on their structures to help optimize the performance. And I'll stop there. And thank you very much for your time listening to me. Thanks. Fantastic.
Okay, so we've now got time for a few questions.
I'm just curious, to what extent does the time of year of deployment of the structure influence the final assemblage by our community?
So, and I'm referring to published papers on this. It has a significant effect at the beginning, but biofouling communities tend to converge to a stable community, if you like, further down the line. So from an engineering perspective, that's about 2 years. So engineers are interested in what biofouling community will be at the 2-year stage once the fouling is quite well developed.
So there'd be no benefit to a structure that's maybe being brought in every 12 months for maintenance in setting a time of year when that changeover is done?
I think the benefits that could potentially be got from that may be outweighed by other commercial interests that they have. But I do think that if you're developing in a certain area, you need to be aware of the types of communities which might be dominant on your structure. Yeah.
One at the front again.
That was great. I think it's also really important, not just from a turbine perspective, but also from some of the environmental monitoring sensors that are potentially going in here. That the biofouling can have a huge effect on those. So I was just wondering, are you also looking at sort of potential ways to reduce some of that biofouling?
No, there's a huge industry out there for looking at coatings and ultrasonic gizmos. I think from my perspective, I'm taking the angle that engineers should design their structure to withstand these extra forces, or at least undertake maintenance regimes which reflect the risk involved in that biofouling community. We're talking about structures which need to be in the marine environment for up to 10 years. That's not going to happen in the first wave of renewable energy devices. But for renewable energy industry to be successful, the length of time that structure is in the water needs to be increased. And a lot of the anti-fouling paints aren't quite there yet to deal with that kind of length of time of submersion.
At the very back. First in the middle, and one last question.
Hey, that's just to consider how long it takes to stabilize. We've done some ROV studies on turbines. We've done them annually, burn a lot of sand.
Yeah.
So we had mussels. First time we went, we had really pictures of mussels and pimos on. And the next time we went back, it was just a small amount of mussels, and then it was scoured with a lot of sea squirts.
Yeah.
Yeah. So it made a massive it changed in 2 years?
Yeah. Yeah.
Just summarise the question, please.
I'm going to try. Yeah. So to summarise the question, it's, we're talking about scour here and how scour affects biofouling. I think from the work that we did, we selected navigation buoys for 2 reasons. Because there's no artificial structures that are in some of these very high flow environments at the moment. So that's a good starting point. But also biofouling tends to be thicker, heavier in the upper reaches of the water column, and it's not affected as much by scour. So it's, if you like, the worst case scenario, and that's why we selected it. However, it is very different from a benthic mounted tidal turbine, because we're outside the photic zone, so we've got no laminaria, no kelp, and so in that scenario, we just need more data, more structures, more surveys. Yeah, it's early stages yet.
Okay, thank you very much.
Brilliant, thank you.
Okay, for those of you who still have questions, scribble them down and we can ask them at the end of all the speakers. So next up is Callum Penny, who is an IT core research engineer, and he'll be talking about how to mitigate sea growth.
Great. Good morning, everyone. Thanks for the opportunity to talk today. I think my talk follows on quite nicely after Adrian's. So yeah, without further ado, I'll just be talking about the marine growth on Alberturn's wave energy devices. So first, just kind of going to give you a brief introduction to Alberturn and the WaveNet, kind of how the wave energy device operates, and then I'll be talking to you about this, which is our Kishorn test deployment, where we have 6 devices in the water connected in a triangular grid. And we went out there, this is 2 days ago, conducted an offshore survey, edited the footage at 2 a.m. last night. So printing you some quite fresh things, and then looking at the marine growth on that. So this is the WaveNet. Essentially, it's a modular, scalable wave energy concept. So a single unit is a squid. You connect multiple of these units together to form a net. So the idea is that it covers a large area. And there's just a little animation there in the corner showing how it works. And just a little project overview about Kishorn. Loch Kishorn is in the inner sound of Skye. It's in the Northwest Highlands. It's a sheltered sea loch, so it's quite a good place for a wave energy nursery. Wave conditions there, typically about 0 to 0.5 meters significant wave height. And as mentioned, we have 6 squids deployed in a triangular mooring grid. And that blue box there in the corner is a horse box converted into a mobile power station. So kind of just excuse the cheesy jazz music. I thought I'd hope to keep you all awake. But here's the footage from the offshore survey. Oh, it's not playing.
It's on the main screen.
Sorry. It doesn't really need music, hey? I could just talk through this actually. This is Power Takeoff 4. So this one was actually significantly cleaner than the others. So it's kind of important to realize that they were all deployed at different times. The longest ones have been in for 8 weeks. A couple have been in for 7 weeks. This one has been in for 4 weeks. As you can see, it's quite clean. This is, I think, squid 4 next to squid 5, also known as dirty squid. It's just absolutely covered in growth. I think this one is squid 6 against squid 3. Quite interestingly, squid 3 has been in for 8 weeks, but it's totally clean. No explanation for that. We're not using any different paints or anything. So we lost him. Yes, so just kind of discussing these results. Essentially, what I wanted to display was that we have, an array of 6, but we've kind of got different, varying levels of bearded, hairy dirtiness. So kind of looking, and some of this doesn't make sense. Squid 4 has been in for 4 weeks, and that's the cleanest. but squid 3 has been in for 8 weeks alongside 6, and 6 has got a grey beard and 3 is clean. So that's one thing to point out. And I thought it was interesting to also kind of contrast these results in comparison to our previous Isle of Muck deployment. So on the left we have squids 2 and 3 being retrieved from the site after about 5 to 13 weeks of service. On the right we have squid 5 retrieved from the Kishoran site. Granted, after 27 weeks of service, but that's a significant amount of growth. Kind of looking at dirty squid in a bit more detail, just everything grows on it. And there are multiple materials here, moving parts. Those are hydraulic hoses, high density plastics, cast iron, aluminium, and it settles on everything. And so this is 6 months worth of growth. And as Adrian pointed out, this changes the drag damping and also adds added mass, so it's altering the operation of our devices. So to kind of look at this, what we observed, squid 5 was in for 6 months. It was taken out in July, given a clean with a pressure wash and redeployed, I think, a few weeks later. And it quickly re-established its marine growth colonies. The growth came back even faster. Squid 3 was an anomaly. For some reason, it just didn't have any growth on it. And we also obviously noticed, as expected, that growth rate increased during times of stillness of no service, where everything was able to settle better. One positive observation was that the piston shafts were kind of almost untouched, except I think on dirty squid where there was some small barnacles. So does this matter? If we're in a more energetic site, will the marine growth actually decrease? Will the pistons be moving so much, and there's scrapers on these pistons to remove the growth before it actually settles? Will it become an issue? And so possibly we need a monitoring regime to inform scheduled maintenance. But even if we are maintaining it, is there a point in cleaning it? Because as we saw with squid 5, it rapidly regained its growth. So finally, just to conclude, the issues we're getting from the marine growth, it creates friction at the joints of the pumping modules. They're settling on the pistons, which might cause potential damage to the seals. That's not the common grey seal. That's the piston seal. I know it's a room full of ecologists. And finally, it alters the properties of the mooring system and the buoyancy modules. So opportunities. Obviously, we're interested in mitigating this, and so it was proposed to install an ultrasonic transducer nicknamed the death ray. And they typically install these on boats, and we don't actually know if this will be effective. So we've only just installed this. We'll be implementing it now on dirty squid, and I think finally it would be interesting, say, looking at things Jen's and Adrian's work again, looking at the spatial and temporal variability. As things change with seasons, and looking at kind of geographical distribution. But that concludes my talk. Thanks very much for listening.
So we'll take questions at the end. So next up is Sally Rouse from SAMS, and she'll be talking about benthic productivity on artificial structures.
Thanks. Okay, so I'm a PhD student based at SAMS, and the focus of my research has been looking at benthic productivity on artificial structures, specifically in relation to renewables. So I'll just give a really quick overview of my project and how some of the results might feed into engineering considerations. So as everyone's aware now, when renewable infrastructure goes into the ocean, it has the capacity to act as an artificial reef. As with any hard substrate, it provides shelter and an attachment point for marine organisms, and that means that some of the natural processes that we get in the ocean that are listed there might be replicated on the renewable infrastructure. And with the replication of those processes, we can actually get ecosystem services arising from the infrastructure, such as the provision of fisheries. The ecological functioning of artificial reef communities is still quite poorly understood, and in particular, there's debate whether infrastructure simply attracts surrounding biomass or can actually sustain new production. And one of the key parts of understanding this debate for specific renewable projects is to look at the capacity of the infrastructure to sustain resources at the bottom of the food chain, which would then feed up to higher species. I'm hoping if we can begin to understand that, then we can move to a situation where we can predict for individual projects and infrastructure associated with renewables that in certain types of environments will have X kilograms or grams of biomass produced per year. So the first stage in answering this question is trying to quantify the relationship between structural aspects of renewable infrastructure and the resulting productivity, and then understand how that relationship between structure and productivity actually varies according to the type of environment that you're in. And they're really the two aims of my PhD. And I've been trying to address those questions at the Loch Vinny Artificial Reef Complex, which is an experimental series of 30 reef units based on the west coast of Scotland. And you can just see that here they're arranged into 5 groups. And we have a current gradient running across the site with lower current exposure down here up to higher current exposure in the northeast. Approximately half of the reef modules look something like this, so they're made out of blocks with the 2 points in, and then the other half of the reef modules are made out of this solid block you can see there on the right. So we have varying levels of habitat complexity, and this structure is functionally similar to some of the scour protection material you might get associated with renewable developments. So to look at the question of productivity, I've been transplanting a bioindicator filter feeding animal to different locations on the reef, within the reef, and to the reefs in different locations. And I'll just whiz you through my main findings. So we found that the reefs that are located in mid-exposure current regimes actually have the highest associated productivity, and that then drops off from the lower current ones to finally the reefs that are in the highest current exposure actually have the lowest associated productivity. The total productive output of the reef is made up from productivity that's associated with internal areas of the reef, so between the reef blocks, and productivity that's associated with the periphery. But that relationship between the internal areas and the total productive output actually varies according to both the type of environment that you're in and the type of block. So in low current areas, the internal area is actually only contributing 4% of the total productive output of the structure. And similarly, the simple reef blocks, the internal areas don't contribute so much. So the next stage in this project is to understand whether food supply is the driving force behind these productivity patterns, and if so, whether we can use patterns of food supply, which are determined by the particle concentration in the water and the flow regime, to predict the resultant productivity. So the last 2 talks have kind of been talking about these associated communities as being a problem for the device, but on certain types of infrastructure related to renewables, there might be a situation where we actually want to enhance productive output. And if we can understand that relationship between structure and productivity, we can actually suggest modifications of some parts of the infrastructure to enhance productive output. And that might be a way that we can mitigate against the loss of access that fishermen are going to experience around some of this infrastructure. If we can enhance productivity of the benthic organisms, this will feed through into higher commercial species, which will hopefully then move out into areas where the fishermen still have access. So that was just a very quick overview. Just like to say thank you to MASTS, Harriet Watt, and the dive team at SAMS for funding my PhD. Thank you.
Next up, we're moving up on the bend cost into seabirds. This one will be by Helen Wade, previously UHI, now Marine Scotland.
Yes, thank you. So, as Liz said, I've just started at Marine Scotland as a marine ornithologist, but this work is based on my PhD work that I did at the University of Highlands and Islands. So, unlike biofouling organisms and large marine mammals colliding with devices, seabirds are unlikely to have an impact on the ability of structures to actually generate energy. But because of their conservation status, they could have an impact on the industry through the consenting process. And this is because there's uncertainty over the effects of tidal stream developments, and that could cause barriers to developments as regulators take a more precautionary approach. However, there are opportunities to reduce that uncertainty and potentially reduce those barriers by addressing knowledge gaps through targeted monitoring that's informed by baseline survey data collection. So this presentation is based on findings from land-based observations that I undertook at 2 locations overlooking the inner sand of the Pentland Firth, and that overlap to some extent with the Maygen tidal development site there marked in yellow. So surveys were undertaken over 1 month in each season of 1 year, and during which I recorded abundance, distribution and behaviour of birds on the water. And this data was collected in the sites marked there by the red and purple grids. The data was analysed in conjunction with hydrodynamic model data and also considered associations with visible surface features. So one huge knowledge gap is our understanding of underwater behaviour of diving seabirds and also their response to underwater obstacles like tidal stream devices. And one interesting finding from my surveys was that birds are more likely to dive into the oncoming current. And this could mean that birds are carried downstream by the current towards devices whilst facing away from them. And this has obvious implications for their ability to detect and then avoid those devices. So an improved understanding of the underwater behaviour of birds is required, and it could be achieved through a variety of means, including bird-mounted loggers, device-mounted cameras, radar and sonar. And this information could be used to identify the direction that birds are facing in relation to current flows and also their response to obstacles underwater. And one thing to bear in mind, and something that came out of my surveys, is that presence in an area doesn't necessarily equate to risk. So there were seabird species that I in fact saw in my sites that were fully capable of diving to depths that would overlap with tidal stream devices, but they were rarely seen diving there. And this is where baseline data in conjunction with behavioural information can be used to target monitoring and further survey effort on those species most likely to interact with devices. So another knowledge gap is how seabirds use the high velocity current flows likely to be targeted for development, and also their association with the visible surface features that characterise those environments. And this is knowledge that again can help to identify those species most likely to interact with devices and those that might be most at risk. So another finding from my surveys was that not all species forage in the fast flowing water likely to be targeted for developments. And you can see, I hope, from these graphs that Great Northern Diver and Eider never use those high velocity currents likely to be targeted and reaching speeds greater than 2 meters per second, which is indicated by the red dashed line. However, shags and auk species, including black guillemots and puffins, did. And there was also some evidence that auk species may dive to a greater extent in those faster current speeds during the summer and the breeding season. And so this is another example of where species and seasonal level information could help to guide monitoring effort and the species that are targeted. In addition, some species were found to associate with different visible surface features. And so the figure on the left here is or my left, your right, is an example of the current speeds in the Pentland Firth and Inner Sound during an ebb tide taken from a hydrodynamic model. And the warmer colours here represent faster flowing water, whilst the cooler colours represent slower flowing water. And this mix of current speeds and the interactions between them create visible surface features, and these may be targeted by seabirds for foraging opportunities. So for example, you see upwellings and eddies and also shear lines between fast and slow flowing water, an example of which is highlighted here with the white dashed line. You can also see from that top photo how clearly that boundary between the fast and slow flowing water is visible on the sea surface. So one finding from my surveys was that black guillemots may associate to a greater extent with the slow flowing water of eddies. Razorbills may associate with that faster flowing, more turbulent water of shear lines, and puffins may associate with a mix of both of those features. And so this is an area that would benefit from an improved understanding because it could be used to locate monitoring devices like the flowback platform in areas and habitat types that are targeted by species of concern and species that you want to focus on. So in summary, opportunities do exist to reduce the uncertainty over the effects of tidal stream renewable energy devices on seabirds, and this can be achieved by analysing the baseline survey data to then hopefully target further monitoring on those species most likely to be of concern. And this could be a benefit to the industry if regulators are able to make decisions based on improved information rather than taking a more precautionary approach. Thank you.
So please can I ask all the last set of speakers to come up, and if you have now any questions, then fire away.
Come on, Adrian.
Adrian, come up. There's a question in the middle here.
I was there just on the fouling, but one thing that you didn't talk about was bioprotection. So you talked about corrosion, but my understanding is that it's possible that the sea creatures, and depends on what kind of fly ash it will protect the structure, and therefore it might be of interest to the engineers to have the growth. I don't know, it depends.
For sure.
I'm not an expert.
So that particular example I gave to you of the navigation buoy was an anti-corrosion paint rather than an anti-fouling paint, which means it's supposed to last longer because you're not having the leaching of metals into the surrounding water. And that was barnacles which had been cleaned off, and there was other biofouling on top of that. So I think it depends on the situation and the species present, but those barnacles really, you can see very clearly the pitting that's being formed. I would say that that in that particular situation, when you've got barnacles, you're in trouble in terms of the corrosion. I can't imagine a situation where it would help. That's my take on it.
I know this research has been done on this, I don't know if the idea of bioprotection.
Okay. Okay. Well, maybe you could tell me about that.
Yeah, I was very interested in Sally's talk because it seems to me a quite nice potential positive aspect of all of this. And I know the wave industry is in something like hiatus at the moment, and maybe let's just hope that's a temporary thing. But if we start looking, I don't know, 30, 40 years into the future, and if this is a successful sector, which I think a lot of us hope it will be, then we're going to see massive deployments of very large numbers of devices in large arrays. And it seems to me we should be thinking not just about the negative impacts of these things, but what we might do with the engineers to ensure that more positive environmental impacts are occurring. And I just wondered if any of the speakers, including those this morning, have really thought about that. You know, if you look at the scale of potential development in these areas, and marine spatial planning is beginning to identify very large areas that could be developed. You know, what should we be doing as ecologists now to ensure there are some very positive benefits that come from this sector?
I think from a wave energy perspective, a large array would have the opportunity to create an artificial reef. I know artificial reefs have been studied in depth kind of elsewhere, which is static, so kind of dynamic, moving reef. I wouldn't know so much the impacts of. I know there's also investigations into arrays which act as no-go zones for fishing vessels. So hence they kind of turn into is it impromptu kind of de facto sorry, marine protection area, which kind of acts as a stock for fish to grow and populate other surrounding areas.
I'd say it would almost at some point become a requirement if we're going to be putting these structures in and they're going to get closed off to fisheries. I think the only way that that's going to be acceptable to the fishing industry is if you can put these enhancements in to promote fishing in other areas.
Just a comment, I think one of the key things about that actually comes from Sally's work and is understanding, for specific species, what's important for that specific species. So then, when we do that, we've funded a lot of work out there that says that these environments are definitely not the same as natural environments. But that changes based on the characteristics of that environment, as Sally's work clearly showed. And I think now beginning to build in those desirable characteristics, the ones that perhaps support, edible crab species that we really, that might remediate fisheries issues. That's where the really intelligent stuff from the biological side comes in. Is what is it? What do we want to do with these sites? And then what biology do we know about that, and then how do we go about incorporating that into some of these developments?
One way might be to generate food climate models, which we have for the North Sea, for example, where you have the components of biofouling put into that food climate model. So, this is just generating data, but at least you can compare apples with apples and know if you put a structure in the marine environment, you're creating a trophic link, which is useful to higher animals. Equally, you could use it in the decommissioning industry. As you mentioned, you take this artificial structure out of the marine environment, what knock-on impacts does it have for associated species? So definitely lots of work to be done in that area.
Is there a question in the middle there?
Yeah, just got a question for Adrian. I thought it was really interesting that you put up the document from DMV, because I hadn't seen that one before, but I've seen the one for offshore wind, and renewable is really similar, so they give like a general figure to expect 100 millimeters of thickness for devices in the North Sea. And like you said, we wrote that it's very site-specific, it depends on geographic locations, and it doesn't take into account the changes in marine liquid depth either. And developers and engineers use these documents as a Bible basically for standards and guidelines as to what to expect when you put the device in the water. And obviously it's not necessarily reliable for depending on where you're putting it. And I just wondered what your opinion was of the DMV document. And
I'm really glad you asked that, because myself and Ryan are involved in a TeraWatt Project where we're interviewing engineers in the renewable energy industry to find out what their principal concerns are with regard to biofouling. And then from that information, we're working with PML applications to look at sensory tools and also predictive mapping tools to better inform engineers. But it really has to be engineer focused of what their problems are, and then we can start saying, well, we've actually got information on the thickness, the density, and we can improve on best guess. So that's really where we're taking things at the moment.
I just quickly pitch if there are any engineering types in the room that are interested in contributing.
Thanks very much.
Adrian and I.
Yes, question for Helen, please. I wondered, on the basis of what you just presented, could you comment on seasonal variability, perhaps, in cycles which you find in species of birds, which you're seeing changes in how intensity cycles are used?
Yeah. So there were some species that definitely occurred at different times of year. So, for example, Great Northern Dive were only there in winter. And so, yeah, I think that's definitely something that needs to be considered, and particularly this kind of idea that some of them may be diving in those areas to a greater extent during the summer, during the breeding season when birds are already under a huge amount of pressure and potentially foraging more, which will increase their risk of overlapping with devices anyway. And that's something that I think we're only just beginning to touch on. So yeah, there's definitely seasonal variation, and seasonal variation we wouldn't expect it even within resident species like shags. They were there throughout the summer. No, they weren't there in the summer very much, but they were there throughout all other seasons, which was an unexpected result because you would expect them to be there.
You said the diving seabirds dived into the tidal current. That's quite a very important observation. I was wondering how you measured that and how you know that they do that underwater.
Well, it's purely based on above water observations, which is a caveat because obviously we have no idea what they're doing underneath. But I mean, I think that's something that's really simple to collect and could be easily incorporated into surveys of sites, because I literally, I knew which direction the flow was going because it's very obvious, and was it going with the flow or against the flow, yes or no. But it is something that we can only see from surface observations, and some of the evidence indicates that they surface with no particular direction preference. And so what are they doing under the water? Are they turning, are they staying facing into the flow, or are they moving around? And that's something I think we can only see potentially with cameras underwater or loggers attached to birds with compasses on them and accelerometers to see what they're doing. And yeah, but it was an unexpected and interesting thing, because the level of collision risk of the birds facing away.
Important to catch that, because yeah, I can imagine they could orientate close in the surface, but if they're just going
Yeah.
in surface behind them, obviously, like I said, diving in, if they are swimming into the current, then I guess the potential for impacts is less.
Yeah, definitely. I mean, if they're not facing in the direction of the flow, they can't see the devices if that's the method that they're going to use to detect and avoid. And in theory, they maybe have more control if they dive into the current, because you can imagine if you've got a tailwind or a tail current, the potential is they're not streamlined in that backward direction, so perhaps they have to swim against the current to maintain some level of control.
Just to comment on seeing the devices if they ever. It's obviously in the marine environment, sight isn't the primary kind of sensor for where things are, and fish when they're swimming in shoals have the ability to detect pressure changes. Mm-hmm. So I don't think it's an issue of kind of being blind to where the tidal currents are. I think they'll be aware. Sorry, the tidal turbines. Yeah. They'll be aware of the tidal turbines, but being able to control being sucked into the wake, that's another issue. Mm-hmm. But they definitely know they're there, I think. Is the point.
Okay.
Mark?
Helen, just to follow up again on the diving the maker aspect, just wondering about where the prey selection comes into that, because things like guillemots will be diving down to the bottom mostly on into is that right?
Liz will know more than that.
So they're going to be doing something rather different than something that's going for pelagic species such as a raven. So that while the point about taking off into the wind, I think that there's a certain kind of logic to that. Yeah. But actually what they're doing in the water is going to be very much dictated by what they're hunting on.
Yeah, and
so that I was just wondering actually as well whether there was the different species, that uniformity of dive aspect was kind of there, or did it vary between the species, and could you link that to what their origin was?
I couldn't pull the species apart to look at different species. I didn't have enough observations, but that, yeah, I'm sure there are differences, but on a hunch, actually, thinking about watching them, most of them tended to dive in. Shags, black guillemots, puffins, they all tended to dive into the flow. But that's not borne out by the ability to do any statistics on that. In terms of the prey that they're foraging on, that could be dictated by the habitat that they're foraging in. So, for example, black guillemots, I said they were often in the eddies, but actually they were sometimes right up against the shear line foraging. And so whether they're using the shear line as a functional barrier because of the turbulence, there's evidence that marine mammals do that to facilitate prey capture. And also in terms of whether they're pelagic or benthic will have a different, depending on the device that you're using, is obviously going to have an impact on their collision risk, depending on where in the water column they are. So.
Jen, you have a question?
It's a question for Adrian and probably Hannah a bit as well. Most of the biofouling work that's kind of been done so far has been on standalone proxies or individual renewable energy devices. We're moving into a world where we're starting to get arrays, starting to be thinking about being deployed, and we're starting to start thinking about that more complex environment. Do you think an array situation will mean that you have increased biofouling due to more increased larvae or anything like that? Do you think it's going to make a difference? It's something we need to start thinking about in our biofouling calculations.
So one of the things I was really interested in with the navigation buoys is I was particularly interested in the fact that you might have a different biofouling community on a tidal energy device than you would on a wave energy device, even though you're dealing with very high energy environments. So we targeted some buoys, for example, Black Rock, which is a buoy in the Sound of Isla, where there's developments going on. And actually, across large geographical areas, we didn't see this signal of biofouling communities being very different in high compared to low flow environments. And I think that was because the presence of large kelp forming species changed the boundary layer characteristics so other species could live in that community. So in terms of the array, changes in flow characteristics might be important for larger species, but on a small scale, you've got to think about the scale of a barnacle's operating at. You might be in 3 meters per second water current, but the boundary layers conditions are such that you can live there anyway. So I know it's a long-winded answer to your question, but I think we'll have to generate data and see how it pans out.
I have a comment on that. It's an interesting point. I haven't thought of it before. How the size and scale of the array would affect the colony. Having a larger array would provide almost a bigger spawning ground for the larvae to kind of colonize. It's best possibly to look at offshore oil and gas platforms and aquaculture. I wouldn't have an answer or a way of predicting and saying yes, there'd definitely be more. Possibly we would reach an equilibrium. I'm not sure what the equilibrium is. It's probably a point of saturation where there just can't be any more marine growth because all the surfaces are covered. And if we already have single devices in the water completely covered, such as dirty squid, so it's already hit saturation. You can't really have more. They start joining between devices, but it's an interesting point.
Oh, is yours carrying on?
Yeah.
Okay, go.
But it's just really quick. I think the other thing to think about though is even scaling up to arrays is how big actually is that surface area and how much larvae does it actually contribute to the overall larval pool. And in the case of an invasive species, maybe that's really important because that wasn't there before. But I mean, a typical barnacle spawns, I don't know, like 10,000 eggs. And you think about that as one barnacle. Okay, well, and how many barnacles are in a square meter? Now, how big is our rocky coastline versus, so I'd actually love to do a back-of-the-envelope calculation about that, because I often wonder, beyond the engineering issues around biochar, which I think are really important, in terms of I guess, artificial recreating that habitat. How big are we talking here anyway? And Andy Little, the MOD guy showed the slide of all the wrecks around the UK coastline in the decommissioning workshop yesterday. And if you look at that compared to what we're talking about in terms of renewables, even if we fill up all of the licensed areas right now, I mean, the scale is just completely different. I think it's really important in terms of when we talk about biomass and all these things, to really keep that in mind. It's hard to do. I mean, we need to do a better job of communicating that scale to the wider public, perhaps, as well. But that's just my opinion.
Kind of following on, maybe not quite following, but something based on something Adrian said, something Callum said, and something John said early on, going back to thinking about, say, the squid and the timing of recruitment of, say, barnacles. And there's a particular window where they spawn, and then the larvae settle, and then could settle. If you get a settled period, like say like now, big high pressure sits over the UK for a week and a bit, something like that. Could you end up with a device that's found in all the wrong places, effectively? Because you sort of mentioned that it might be freer on distance and things if it was in a wave size. This is a scenario where you might end up with really kind of stochastic effects you might not expect just because of the way a weather system sits over the country at the wrong time.
That's definitely an issue, is these periods of static waves. I think we're actually looking into designing a collar so that the piston shaft is no longer exposed to the marine environment. Because if they settle, what we have in the piston shaft is a preliminary scraper tool, and barnacle goes straight through that. If it's given enough time to settle and grow, I don't know the growth rate. There's a scraper and there's a main seal and possibly a backup seal. That's definitely going to cause issues. So we might need to engineer this out completely by looking at, say, a collar to isolate the piston mechanism. Or we might need to be looking at anti-fouling paint. There is anti-fouling paint on the squid. It doesn't. I don't want to say it doesn't work, but there's definitely fouling on it. So.
Can I just ask a bit anti-fouling paint, because I can see there's two different kinds of structures that we're putting in the sea. Some of them, like say the Regen foundations, will get put down, stuck in there for 25 years, and they can get hopefully demolition. Then there's the equipment we put down, which we might
pick up with a boat and refurbish, maintain, etc. But little larger ones, perhaps the wave generation ones in particular, what is the policy with anti-fouling paint? Because if I were an engineer, I would think, great, it will last for a year, it will reduce biofouling, but I can imagine the environmental side, if you start putting anti-fouling paint on all these structures, then that's not such a good thing. So I suppose my question is, what is practice and policy in relation to anti-fouling coverings?
So in terms of renewable energy, I would refer you to the REDAT project that looked at different anti-fouling coatings for a gravity-based structure, so it had panels in the Falls of Orness. So the report is quite difficult to find, so I could send you a copy on. They are trying to phase out copper-based anti-fouling paints, but I'm not aware of any policy that states you've got limits on what you can use. I might be wrong with that. Perhaps somebody here could enlighten me.
I just got a write into that. I think I'm hearing years ago. I heard that it was almost anecdotal that the degree of anodic protection afforded to devices underwater could actually dramatically affect the biofouling. Somebody pick up on that and say that I've heard of it, or what I'm saying is wrong.
That used universally by the oil industry on its offshore pipelines, for example, but also on structures.
Oh, sorry,
it's used almost universally by the offshore oil and gas industry on its pipelines and its structures. So it's using sacrificial anodes to effectively create a protection system. As far as I'm aware, no marine renewable device is actually considered using these systems, but I might be wrong.
That sounds a bit daft, if it works well enough.
There are a couple of zinc plates strapped to each arm.
There are, right?
And I don't recall on dirty squid, but on squid number 4 they were clean. So I don't know if they affect the anti-fouling, but we do have sacrificial protection around it. Yeah.
I mean, it's more to protect against corrosion.
Yeah.
Just to follow on to that, they're definitely used in offshore wind as well, on the outside in the transition piece and in the inside. And as far as I'm aware, they don't seem to get covered in fouling. I think they must have. There's something about them.
So you're talking that the actual sacrificial anodes themselves don't get covered in fouling?
They're toxic, yeah.
Yeah, yes, because they by their nature are sacrificial and they will just. I was referring more to, it was an anecdotal, that's simply just Antarctic survey, that anodic protection did influence the biofouling community on the metal that was being protected. That was anecdotal or just a story.
Okay, so I have a question following on from that space, which is regarding biofouling. How much of the information we previously have from structures is based on materials that are the same kinds of materials that will be used for the devices that we're talking about? So does it transfer?
So there is a fair bit of evidence that shows materials are very important in determining what type of biofouling community. Again, it comes back to what Jonathan was saying or asking, that over time that difference is going to become less important. But yeah, there will be different materials being used in the renewable energy industry, and in particular the turbine blades, for example, composite materials. So yeah, potentially different fouling communities.
From our experience, I'm not sure if the species are different on each material, but as I mentioned, we have multiple different materials used. I've actually showed a picture of include backtrack, but there's plastics and I can't really go back. There's plastics and cast iron and all sorts of. Oh, it's not even going back, is it?
Yeah, that's it.
Oh, it is. Sorry. There's all manner of material on it, and everything is covered, bar the anodes. Here we go. So It's really not a nice sailfish, but this is rubber. Here it's rubber to protect the end stops. This is hydraulic hose. This is high density, I think it's high HDE, high density plastics. Cast iron joint modules. I think the only things, so we do have a couple of zinc components down here. I think they eventually got covered. Maybe there's settlement on particular material, which they can kind of use as the initial point in settling, and then colonize everything else. But as far as that goes, I don't think there's much bias.
Barnacles are particularly good to settle.
Yeah. Can I ask then, sorry, do you have any biologists? Did you allow anybody to come up, at least take pictures and biologists to look at the community structures?
No, but they'd be welcome. So,
Anytime, Callum.
I can see why I'm smiling.
Yeah, collecting barnacles is a thing,
On that, what's the difference between the Isle of May site and Keystone site in terms of like what's the is one more weighty than the other one? Is one more exposed than the other one?
Isle of Muck is more energetic. I'm not sure the operation is, but in Kishon you get periods of calm. I think last weekend was calm for about 5 days at a time, and even then, it doesn't really get stormy up there. So this is from a sheltered sea lock. Sorry to show off a little. The ones on the left, those are from muck, and there hasn't been much opportunity to settle. But the ones on the right, the squid on the right, that's at a calmer site. So I think, maybe the productivity of the seas are the same. It's just the fact that the squids on the left are kind of in a more energetic environment that's changing the rates of settlement.
Any more questions?
It's not a question, it's a general remark to anyone here. Just realize that we don't know anything. Just scratching the surface of the interaction between engineering and hydrogen structures with environments. And we have seen a beautiful first results of how this affects whales or dolphins or seabirds. But as a veterinary ecologist, I would like to see more about how these things interact with plankton or larvae or with lobsters and crabs. So I can see that we're going to need each other in the future quite often. And please, let's start something with strong collaborations between engineers and ecologists. We need to figure out we need these structures are not far apart. And the collocation of these things, it's going to be necessary, not only of matters of energy or ecology, it's going to be beneficial for costs at the same time. So we have to figure out, try to make out the best of it. So we need you and you need us.
Hence this workshop.
So if I can go on from that, I'm just wondering, we have a lot of people in here covering up a lot of range of companies, of the potential companies. Should we be talking about a location to start this in terms of at least data sharing and an actual location? Adrian, you just mentioned the REDAP project's hard to find, these sorts of things. That, can we ask perhaps the catapults in the room and the OGIPs in the room that perhaps a data portal, maybe just linked to the Marine Scotland interactive portal since it's already up and going, but that there is somewhere that these types of data that we know exist already, like Adrian's maps of communities, could potentially be a one-stop to initiate the amount of interaction we should start to have between each other in terms of being able to look at funding and go forward.
That's what it's like. But we host the Wind and Tidal Knowledge Network, which we set up at the county state. And it's kind of at the moment, it's a collection of about 1,500 documents focused on wind and tidal, and it includes a mixture of documents and data sets. It's by no means public. We picked it up from the county state. We want to improve it to make it more usable. We'd like to get as much information into it. It's there. If you want to submit stuff, we're more than young. We'll put stuff on it. what we need to do is to improve the interface and actually understand what people want to get out of this as well. But absolutely, we're more than happy to talk about that. It's not as used as well as we'd like it to be used. I honestly don't know if that's due to the content or lack of content, or whether people don't know it's there, or because its user interface isn't as slick as it maybe should be. So any feedback that you've got, I'm happy to. If you, it's the URL, it's something like Women Town Knowledge Network. If you search for Women Town Knowledge Network, you'll find it. It's not hidden away anywhere, and we wouldn't have to post documents or archive documents. People can't find anywhere else.
Just to add to that, we're keen to explore free online tools, just very simple tools to inform engineers, for example, on the characteristics, so that a common question is, what's this unwanted stuff on our structure? What characteristics does it have? And it's very easy for us to make these kind of tools and make some kind of impact. Because if you've seen from some of the responses to our questions, biofouling is just so many factors could influence the type of biofouling. Maybe we just need to work towards a more observation approach to the science, get the kit in the water and observe what's going to happen, and say something sensible about stuff that's growing on the structure.
And middle back.
You mentioned how you estimate the density.
Yeah.
From our training data.
Yeah. Well, those were from photographs taken. So that was the proportion cover of different hard fouling species, and we measured density of that same patch of biofouling.
How did you measure the density from your source? You measured the
I didn't have to. I had the full sample, so I just weighed the sample, and then I made a plastic tube, put the sample in, measured the displaced water from that. And actually, when I did that method, I made a mistake because, and I think it's a mistake that's been made throughout the DNV guidelines, that I didn't include the amount of entrained seawater in that biofouling sample. So those density estimates actually overestimate. When you do the combination of thickness, the underlying geometry of the structure, you actually overestimate the weight on the structure. So there's work to be done there to improve that method as well.
Okay, we've got time for a few more questions. Are there any fronts?
It's more of a building on what Beth said. The issue of data and data sharing and what's available, but also focusing on questions and what questions can we answer and what can't we answer. So I work on birds, and I'm seeing the work that's been done, and some of it's really cool and really interesting. I haven't heard a lot, that's great. But then there's whole elements that are much more difficult. And actually a lot of the tidal areas, it's a very difficult place to work on. Sorry Liz, I don't mean to say that to you because you know far better than that. It would just be very helpful to think about what questions we can answer and what we can't answer.
Yeah.
So thinking about just the birds for a second, that's really nice site-based work. But questions revolving around population level effects on SVAs, which is where a lot of the impetus has to come from, is much, much more difficult. And yet, I don't know, this has probably already been done, but to what extent do we have that series of questions and whether we can answer them? Because that seems to me a good focus rather than just data, and to have to start with your questions. See, are there some sites where we have better opportunities to answer them?
One comment on that as well, and Beth will back me up on it, hopefully. The work that we've done with Beth and James Waggett and Alex Robbins, at this point, we haven't found consistencies in behaviour and interactions across sites. And that may be because of methods that have been used, so different methods at different sites, so then the data isn't comparable. But at this point, we're not even seeing consistent behaviour across sites. So yeah, examples of sites where maybe you collect more data is useful, but also we need to bear in mind that they maybe not be using sites in the same way in different areas.
Yeah, I think you're right. It's kind of drilling down into, if we have a limited pot of money, wouldn't that be really nice to know? But actually, it's just so infeasible that it becomes close to a waste. Can we focus on? I don't know how close we are actually to seabirds to be in there. I know Beth has kind of started that process at one point, but I think we need to do more of that. To really truly get to the point of saying, okay, well, if we can't answer those, what's the next ones? What are the next ones that feed into answering those wouldn't it be nice questions, and focusing on the ones where we actually trust that we can get some solid data and some answers.
If I can chip in, I think what we've got here is we know that Origin report sitting there with all of us community putting our what we've got to do right now questions in that one, although some of the questions, some of the issues that have come up today probably aren't in there, so I don't know if Ian's in the room or not, but I know he's around there somewhere.
He's not here, but he said he'd like a copy of the report from this workshop.
But Andrew's here as well, so we can feed that back in, that what should we be doing right now, what are the immediate things. But then there's the next layers up of the population effects that Francis has just mentioned. So we as a research community, of course, are looking at our ranges of funding to ask these questions too. So should we be, as a community, looking a little bit more at that next level up of population, so where we're going to get funding to do that, say just in UK waters, and then looking up even one more level of EU type of funding to think about this community getting better together with potentially our North American colleagues as well as our European colleagues to answer some of the comparative questions that not just on our sites, but sites across the world. And so I'm hoping, I'm sure all of us in this room are doing that, but hopefully if we can have a little bit more focus on those via agencies such as Catapult and Origin to help with those, that would be extremely helpful because I know how busy everybody is. But these are definitely new topics in terms of things that have come up today that I don't think are quite as much on the radar as they should be. So we will just report to Ian.
Oh, Jen.
Yeah, I just wanted to kind of add a comment onto that really. I just wanted to say how absolutely brilliant I think it is that we're kind of having this open conversation about things like bioplanning as well. So I've been going to a number of renewable energy conferences in the last couple of years, and it's something that it's like the dirty little secret that developers never ever speak about. And actually it's really, really hard to get data out of people to work with them because it's something that hasn't really been coming up for licensing. It's an operational problem. So they're starting to encounter this problem now, but it's almost like they're embarrassed about it. It's like, it's okay, everyone gets barnacles, don't worry about it. It's great to have California to kind of like actually show some pictures of a biofoul device, you know, it's starting to pop up, but they're still pretty infrequent, and I think it's really important that we kind of do spread that word out there that it's all right, biofoul is normal, can we please talk about it, can we see what you're getting, and can we kind of see if we can actually come together as a community to kind of come up with some solutions to how this is working. I think we're getting now, I've probably got about half a dozen developers on board now where I'm actually getting to play with their biofoul, which is great, but there's still a real kind of stigma attached to it. It's really weird, so I think it's great that we're talking about it, and I think the more reassurance we can do to engineers and to developers, the better, so we can actually get this information openly shared.
I think great comment, Jen. To kind of look at this as, you know, an opportunity for developing solutions rather than something we should be ashamed and embarrassed about, because, you know, showing our dirty pictures on. I think you know, that's kind of like we should be shining on it. It's you know, how can we engineer solutions to, you know, fix this and share that amongst people.
Okay, so thank you for your questions. Thank you to the speakers. If we can thank them once again, and then I'll hand over to Beth.
Okay, well, thank you all for a fantastic morning. I'll try to read my own notes here. So I'm just going to do 5 minutes of summing up, and then we're going to run off for lunch, and we're going to be back here at 1:30 for the TeraWatt afternoon. Okay, so I think what we saw was a fantastic opening of really starting to understand using modeling of interactions with tidal turbines and with soft targets or soft tissues. And this concept of also, whoever brought it up, that being able to actually go within that and have different types of tissues and look at things like spleens, you know, that usually in a car accident with humans, that's the problem. It's the speed of impact and stuff. So really good ideas coming up through that. Looking at more data to use to identify all of these biological impacts and interactions. So things like looking at fish and fish change of behavior. The ideas coming up about blade changes and speed changes. You know, that would be fantastic to understand if the modeling community is actually looking at different shapes of blades and what that might mean, or, you know, is the shape of blade that's been used so ideal already? Like, we don't know as ecologists. Is that been the evolution over many, many years to the perfect blade, or is that just something that the community started off with 20 years ago and has stuck to it because that's what people will give the money for because it's familiar? You know, I think we'd like to know that kind of information to the ecologists. So are we suggesting silly things when we suggest these things? Will we go to, you know, the more industry-oriented conferences and be laughed off the stage because, you know, the cost implications are so horrendous to change now? So it'd be really nice to know from the engineers in the audience if you can let us know, are we looking stupid when we ask these questions? So the whole idea then also that all of this feeds back in, and that people within Catapult, within ORCHIP, within our other national funding agencies are aware of these questions, are aware of what we're trying to ask, and are aware of the information that's coming through quickly being put out. So that was our first bit of the session. So our second bit of the session then is the idea of these maps of communities and all the biofouling, the confusing variety of fouling on different instruments. Why are we having such differences with instruments sitting beside each other? But really that positive growth idea, the idea of using this as potential areas to actually harvest things from. I know the wind industry is considering things like oyster grounds and stuff like the North Sea, where it's called the oyster, help me out here, the Marine Scotland people. There is an oyster ground. There used to be oysters there. Now there's going to be wind farms there, and they're thinking about reseeding the natural native oyster in that area. Nobody mentioned it, but, you know, kelp farming as well. I don't know, is that just too heavy to even think about, and we shouldn't be going there. But the idea is that some of these wave devices look like perfect kelp farm. So, and then the seabird behavior, as Helen was saying, and behaviors of the mammals and fish species. We are just scratching the surface, especially in these high energy areas. But hopefully a lot of these species are like indicator species. So what Helen is showing, you know, if a certain type of bird only ever feeds in sheer areas, can we use that type of species for the engineers to say, you're going to get a lot of shear in this spot. Do you really want to put a turbine here? Because we've been observing birds. It's nice and cheap. You didn't have to put an ADCP in the water to figure that one out. You know, should we be sharing that kind of information? So essentially it does come down to a lot more of this sharing of information, this knowledge exchange. Really happy to see this big room full of people who are interested in this, but obviously it needs to go farther. So all those last bits of conversation, yeah, how do we take this farther? How do we get all the information we know exists already up and to the right people and people aware of it? You know, please do your best to tell all the rest of your colleagues, but obviously we need to do some actual on the ground getting this information up on websites. So I will stop there and let people go off and have a lunch, but please be back here at 1:30 when we start the EcoWatt. Thank you.